Our first presentation for today and our next for the program is on statistics and probability theory. And originally, this was scheduled to be a duet. However, because of weather issues and flight cancellations and things of that nature, it's going to be a solo. And I can feel for our speaker, Hal Stern, because several years ago, I was asked to moderate a panel at Northwestern, and I made it through weather to Chicago, but the panel didn't. And so being resourceful and finding that out when I got off my flight that night in Chicago, I went to an H&M and purchased a box of socks and drew little faces on the socks. So we did sock puppets. Hal is more, I guess, more daring than that. So absent sock puppets, our next speaker is Hal Stern. Hal is the Chancellor Professor in the Department of Statistics at the University of California, Irvine. He came to Cal Irvine in 2002 as the founding chair of the Department of Statistics. He served for 8 years as chair of statistics and then 6.5 years as dean of the Donald Bren School of Information and Computer Sciences. Prior to joining the faculty at Cal Irvine, he had faculty appointments at Iowa State University, and Harvard. Within statistics, he's known for his research work in Bayesian statistical methodology and model assessment techniques, and for collaborative projects in the life sciences and social sciences. His current focus is on the application of statistical methods in forensic science, and he is a co-director of the NIST-funded Center for Statistics and Applications in Forensic Evidence, and also serves on the Physics Pattern Interpretation Committee of the Organization of Scientific Area Committees, or OSAC. Please welcome Hal Stern.
Thanks, Matt. So what we learned from the introduction is I'm not as creative as Matt. That's number one. A couple of preliminary remarks. So as Matt mentioned, this is kind of work I do with Alicia Karakwiri, who's the director of the Center CSAFE at Iowa State University, and she was at the AFTE meeting, the Firearms and Toolmark Examiners meeting in Nashville. The presentation I'm going to give this morning, and then the second half this afternoon, which are labeled in the program Statistics 1 and 2, are based on a presentation that we developed last summer, just a little bit of background, that we did at the ABA meeting in Chicago for the Judicial Division. And so it was a partnership with a few judges, and what they told us as we talked with them was that to really motivate it, you should have some cases. So we would introduce a case and talk about it, and then talk about the statistics of the case. So that's the genesis of this. When we were planning this, I sent Matt that material. He thought it was good, and a good way to introduce statistics and probability, especially probability for this group. So that's the basis for it. I sent in a set of slides so that we could get continuing legal education credit for this. The slides you're about to see look nothing like those slides. So the bad news is they look nothing like those slides if you studied them or did anything about them. The good news is these are much better. Okay. And I'm more than happy to share these after the fact, if you'd like. A teeny bit about myself, and the first thing I want to do is a little experiment. Can everybody hear me okay?
Yeah.
In the back? Can you hear me?
No.
So close. Okay. All right. Oh, okay. Well, I don't like that either. Okay. a teeny bit about myself, beyond what Matt told you. So I am not a forensic scientist. I do not play one on TV. I'm a statistician. That's all I do. But for the last 20 years, on and off, and for the last decade, quite a bit, I've been spending time on forensic statistics and the role of statistics in the analysis and interpretation of forensic evidence. And we have this research center, CSAFE it's called, and I'll give an update about that later this morning. But so that's kind of that's what informs all of this. And so let me get started. Still in the basic setting the table or context, I think everyone in the room knows this. We find ourselves in an interesting time in forensic science for a variety of reasons. The National Academy report of a decade ago is the top left. The PCAST report is the second one over. They analyzed the state of the world with respect to forensic science and its application in the courts, and had expressed some concerns about especially what we call the pattern disciplines and the scientific foundation for the kinds of statements that are being made. And so a lot of what you're going to hear today is focused in and around that. Of course, there's a number of exonerations. I have something from the Innocence Project website. Also, with about 40% of those having misleading or incorrect forensic evidence as a contributor. And then Matt mentioned my involvement with OSAC. The bottom of the slide are some of the things that have happened since those reports. The National Commission of Forensic Science, the OSAC, attempts to standardize procedures and the like. So this part is where you have more expertise than I, so I won't say a ton about it. But the key points for today is I'm going to try and refer back to this notion of, especially this afternoon, the need for reliability, and in general, and reliability in the case at hand. And all of this has led to the increase of the role of probability in statistics. I've spoken to a number of groups of lawyers and judges over the last few years. I'm always reminded when I do so that many of the people who I'm speaking to went to law school because they had no interest in probability and statistics or anything else mathematical. So I'm cognizant of that. Formulas are, I can't say zero, but minimized. There's one that's central to the application of forensic evidence, the interpretation of forensic evidence. But there should be no tiers, no heavy mathematics, none of that, okay? It's conceptual, but it's real. I'm going to be talking about probability and where it comes from and how it's used and the like. Okay. So, as I said, most of my work has been around what's called the pattern evidence disciplines, and within that there's a focus on what's called the source comparison question. So there are typically two items of evidence, one found at the crime scene, one associated with the suspect, and the goal is to determine if they have the same source. And so lots of examples of this. The picture at the bottom left obviously is a latent fingerprint on the left and exemplar or a known fingerprint on the right. And the question is, did the latent print get made by the same person to whom the finger on the right belongs? Same thing for shoe prints. But even though DNA is not called pattern evidence, the same question arises, right? There's a DNA sample, a blood sample, or a DNA derived from the crime scene, DNA from the suspect. Do they match? And what's the importance of that match? So I guess I do have to open this. It's a little bit easier. And I have to remember not to touch it. Okay. So again, framework-wise, I think everyone agrees on what I have on this slide. That is, if you talk to examiners or you talk to statisticians about how this should be done, they all say we do the same thing, which is we look at the two pieces of evidence, we assess similarities we see, maybe any differences we see, and try to judge whether those observations are likely under first the hypothesis that the objects came from different sources, and then from whether they have the same source. And I have my little scales here. We try to balance those and how that help us make a decision. From there are a variety of ways that gets implemented. And so again, this is all in the form of background. This is a separate talk that I have where I talk about the 3 approaches to the interpretation of forensic evidence. So there are 3 approaches that I think of as common. If you bring another speaker here and say how many approaches, you'll almost certainly get a different number. People parse things in different ways, but the way I'm parsing it for today is, number 1, there is what is the status quo in many of the disciplines that I'm going to talk about, which is expert assessment, expert opinion. So an examiner looks at the evidence based on their experience, training, and standards in their field. And that typically gets summarized by a categorical conclusion. In fingerprints, you only get 1 of 3 answers from an examiner at the present time. There is an identification, the 2 prints have the same source. There's an exclusion, the latent print was not made by the person whose known print you have, or an inconclusive, no determination was possible for a variety of reasons. The second approach is called the 2-stage procedure. In it, there's a first stage in which a binary decision is made. Does the evidence match or not? And once you determine that it matches, it's not always matches, match is not in fact a popular word. Indistinguishable is a popular word. If the 2 evidence pieces are indistinguishable, then we would move on to the second stage, which is labeled identification, a little confusing, but that was by Parker and Holford. And identification in this case is meant to mean, okay, they match, but how probative is that? How likely is it they might match by coincidence, for example? And the third approach is the likelihood ratio. The likelihood ratio at present is applied only in DNA, and really only well in simple DNA problems. But it's the subject of a great deal of discussion. And so I will end up at the likelihood ratio. Okay. So case 1, first case. The first case is not, is very famous within the world of statistics. It appears in a lot of introductory statistics books. And it's called, it's from California, The People versus Collins. And you see a short summary of it here. But the basic description is there was an elderly woman who was attacked, and she remembered something. There were other witnesses who remembered pieces of it, and what came out of the sum of the witness statements was that the attack was carried out by a woman with blonde hair and a ponytail, and then she met up with a black man with a mustache and a beard in a yellow car, and they drove off. And the police eventually were led to an interracial couple that lived in the area that had a yellow Lincoln. So they were charged, and at the trial, the prosecutor said, you know, these are the frequencies of these various characteristics that the eyewitnesses have identified, how often you would see a woman with a ponytail, how often you would see a yellow car in this neighborhood, et cetera, et cetera. And then the prosecutor called a mathematics professor, not a statistics professor. Statisticians make fun of mathematicians, but anyway, a mathematics professor told the mathematics professor, here are the probabilities for all of these characteristics. Can you help us combine them to get the probability of all of these characteristics being found in the same couple? And the mathematics professor used a rule that I'll go into in a little bit more detail called the product rule for independent events to multiply them together. So 1 out of every 10 couples would have a yellow car, 1 out of every 4 of them would have a man with a mustache, 1 out of every 10 of them would so on and so forth. So you multiply them all together, and you end up with a number that's 1 in 12 million. And the prosecutor used this to say, finding a couple like this that matches these eyewitness description is so rare, they must be the couple that committed the robbery. Okay, so that's the setup for this trial. And now I'm going to do a little bit of a detour into probability statistics. So that was the part you were supposed to be comfortable with. Now comes the part you're not supposed to be comfortable with. Every single statistics course that I teach, from the first one to the PhD students, starts with this picture, okay? Because this is fundamentally what goes on when you do statistics in any discipline. There is some population typically that you are interested in learning about, and you are typically not able to see the entire population, so you focus in on a sample. And probability and statistics, two terms Matt used in the introduction, fit into this story in the following way. The laws of probability, probability is a branch of mathematics, what they allow you to do is take information you know about the population and use it to predict or calculate what you might see in a sample. Statistics is the part that goes the other way. From a sample, and what I see in the sample, what can I say about what's in the population? And I have the circle kind of, because that's actually the way it's applied, is we will typically start by making some assumption about the population that tells us what we should see in the sample. We'll look at the sample and see if it matches what I thought. And if it does, I draw one conclusion. If it doesn't, I kind of go back and say, maybe I should change what I thought I knew about the population. So that's the way this gets operationalized. The two forms of logic here, right? Probability is deductive, going from something I know about a population to a sample that I'm going to collect. And the statistics part is known as inductive inference, trying to get from the specific, the sample, to the general, the population. In forensics, it's not always crystal clear, right? This story is crystal clear if you're going to do a political poll. You want to know there's this population of people, you want to know how they feel about something, you're going to take a sample of 100 or 400 or 1,000, and this picture works perfectly well. Not always clear how it works in forensics, but it's there. So for the first part of today, I'm going to focus on probability. Okay. Probability is the mathematical language of uncertainty, and the way that it works is the probability of an event, the chance of rain today, for example, is a number between 0 and 1, describing the likelihood of the event. Sometimes expressed as a percent. When we hear about the chances of rain today, it's 60%, or today it's, I think, a little higher. Then, that's equivalent to saying the probability is 0.6 or 0.8 or whatever. So one little bit of notation that I'm going to use is periodically E or some other letter, if we like, is an event that I'm interested in, rain today, and PR is short for probability, of course. So PRV is the probability of the event, the probability that it rains today. And just to get you to understand our scale, something has probability 0 means it can't happen, won't happen, under no circumstance happen. Probability 1 means a certainty. One thing you should know about me, statisticians don't believe anything has probability 1. You can probably find things that have probability 0, but we never believe in probability 1. Okay. There are two common interpretations of probability. One is as the long-run frequency of the event in a number of repeated identical trials. And so I have a picture, a pair of a dice. If you took statistics long ago, most of you probably did, but have long banished the memory. Lots of examples of dice and coins and things like that. They have the advantage of being easy to work with, fitting into this long-term definition of probability. You can do lots of rolls of dice, but they have the disadvantage of not being particularly interesting to anyone other than compulsive gamblers. Okay, so, the second definition of probability is about subjective belief, kind of my opinion or my assessment. And so I grew up in Queens, not far from Shea Stadium. So this is my first foray into Photoshop. So it says 2019 World Series champion New York Mets. Not likely to happen, but you could say, what's the probability that the Mets are going to win the World Series? So I said there are things with 0 probability, but let's skip that for now. But there's no way to answer that question by reference to the long-run frequency. What does it mean to say, if I played the 2019 season 1,000 times, we do that. I say that in my introductory courses, but it's kind of a ridiculous thing to say. It gets played once. And so that leads to a more subjective view. And we use it all the time, right, when we have to talk about how likely something is to happen, right, in terms of making decisions all the time, right? What deductible should I get on my auto insurance, requires you to think about. You don't think about it this way, but probabilities of accidents and how big accidents and small accidents and things like that. So that's the language. Probability is just our language. And now probability is very confusing. That is, people who study kind of the science of science, as it were, or the psychology of science, have studied and shown people have a very hard time with probability. You can ask all kinds of counterintuitive problems. I was trying to figure out which one to demonstrate, so I'm only going to talk about the birthday problem. A more interesting one, but I decided it would take too much time, is the Monty Hall problem. So if you like probability after this and want to learn more, look up the Monty Hall problem from Let's Make a Deal. But a famous one is known as the birthday problem. Okay? So we have a room here of 40 or 50 people. If I said, what's the probability that somebody in this room shares my birthday? It turns out that's actually unlikely. Okay? It's about 15% chance or something like that. If I said, what's the probability two people in the room share a birthday? That answer, whether you know this or not, is actually remarkably high. Okay. I don't know what it is for the size of this room. I know that the break-even point is 23 people. If you have 23 people, it's 50% that they share a birthday. In 50, it gets up to 75, 80, maybe even 90%. I think it's closer to 90%. It's quite interesting. So probability sometimes acts in counterintuitive ways, is the only point of this question. You don't have to know why, but it does act in counterintuitive ways. The intuition for what's going on is obviously the first one is a specific date. Right? And so it's pretty rare that somebody falls on that specific date. The second allows it to be any date of the year. And so it turns out that it's hard to place 50 people on the calendar and not get through in the same day. Okay. So that was probability. It'd be good if we could stop there, I think. But what turns out to be most relevant for forensics is what's known as conditional probability. So I'm going to take a probability story and then modify it a little bit. The story you're about to hear is based on true events. I looked up my flight yesterday from LAX to JFK, and based on historical data, that flight is delayed 27% of the time, I think, which means it lands 15 minutes or more late 27% of the time. So that's what I knew, right, when I made the reservation. Probability that I was going to be delayed getting into New York was 27%. Now the flight gets close, and I'm not a great traveler, so I'm checking the weather, and I see forecast of thunderstorms in New York. Right? And now, as I'm doing my own personal calculation, I'm saying, wow, the probability I'm going to be delayed now is greater. Right? So more information led me to change the answer. And in mathematics, we formalize that as conditional probability. So I had a probability based on one set of information, and now I update it because I have new information, forecast of thunderstorms. Okay. A little bit more of notation. So there's does it work? Yes. There's a vertical bar here. That's the tricky part now. This is written in words, so notation exists, right? Because it's shorthand. It'd be a pain to write out the full sentence that I'm about to say over and over again. But the full sentence is important, and it's the one you want to know, which is that notation stands for what's the probability that the flight is delayed. Vertical bar is read as given that thunderstorms are forecast. So we can do lots of conditional probability, right? What's the probability that the Mets win the World Series given that Robinson Cano gets hurt? Something like that. So I apologize if you're not a baseball fan. I'll think of other examples. So maybe, and this is where it gets tricky, the 27% actually, I could tell you where it came from. The 27% came from the FAA looking at the last month and determining that 27% of the time this particular flight was delayed. The update that, I don't have the data for that, so that became me subjectively saying, okay, my chances of getting delayed have gone up to 50%. I was delayed by more than an hour, just for your information. Just for your information. How does this fit in with our picture? The first statement, the probability of a delay is 0.27 or 27% chance of a delay, is based on thinking of one population, all flights from LAX to JFK, actually all 11 a.m. flights from, say, so that's the population, and in that case, I happen to have data, as I said, that tells me that 27% of those are delayed. So one way to think about that is the population has a bunch of little airplanes in it. You can think about that circle as having, I should have done this, but I didn't think of it. A bunch of little airplanes in it, and 27% of them are red because they're going to be delayed, and 73% are silver because they're not going to be delayed, okay? The second statement changes the population I'm interested in. I'm not interested in all of those flights. I'm only interested in the flights that occurred on days for which thunderstorms were forecast. Right? So now I get rid of a bunch of those dead planes because they did not occur on days when thunderstorms were forecast. And I look at the ones that are left in the population, and I look at how many of them are delayed and how many are not. Okay? So conceptually, that's what I want to do. And we can't do that very easily in this case, so I made up a number of 0.5, but sometimes you can actually do that. You can have one probability, and you condition and you change the information set that you're working with. I didn't put this on the slide because some people don't find it helpful. In point of fact, what's really going on is all probability is conditional. It's conditional on some set of information that you have. We often start with a very large, not set of information, we start with, in many cases, an absence of information. And so we just think all possible outcomes. And then we learn something that restricts the set. But all probability is conditional on what you're assuming about the population. So that's conditional probability, and we're getting closer to the Collins case. Okay. A couple of things to help us understand conditional probability. So this came from a published article that looked at sentencing of murderers in Georgia, African-American murderers, and the people who were doing the study, trying to determine what factors are associated with this, collected data on all of such cases and put them in a table that you see here. And so, just to make sure we're on the same page, there were 45 cases in which the murder had a white victim and the death penalty was given. There were 85 cases in which the victim was white and no death penalty was given. So that's how this table works. And there are totals around the edges of the table. So if I thought about this as my population, then I could first start by saying, let's think about the entire population and ask what's the probability that a death penalty sentence was given. And it turns out in total, 59 of the 362 cases had a death penalty sentence, which is 16%, probability 0.16. Now I can ask for more specific information. Suppose I look at that only for the cases with a white victim. So this moves me into my conditional probabilities. I focus just on the first row, and I find out that in 45 of those 130 cases, the murderer got the death penalty. So that was 35%, and for a black victim, it was 6%. And so conditional probability, again, changes where we're sitting and maybe provides some clue as to what's going on. This is just really intended to illustrate conditional probability. It's a very simple analysis, ignores a lot of things, and it's not intended to be particularly germane to the subject matter. So sometimes learning additional information doesn't change the answer. So my example here is, I could ask the same question instead of wondering about thunderstorms, looking at what I ate last night for dinner, and say, what's the probability my flight's going to be delayed, given that I had pasta for dinner the night before? We certainly don't think that has an impact. There is this whole butterfly flapping wings thing that, my eating pasta might have changed the world in some way, but it's not very likely. And so when that happens, when you end up in, I won't say good or bad, but when you end up in the circumstance that the conditional probability of a flight delay is exactly the same as the unconditional or the overall probability, we say that the two things involved, the flight delay and my pasta dinner, are independent of each other. So independence plays a huge, huge role in your introductory statistics class and in the application of statistics. All of those examples, again, coin flips, dice rolls, are by definition independent. When I roll the dice this time, it has nothing to do with what came before or after. And so we kind of know just from the construction that they're independent. In forensics, one well-known example of independence is in DNA analysis, we look at markers on different alleles on the human genome. And if you take a marker on one chromosome and a marker on a second chromosome, they are independent because of the way the biology works. And so we actually have real independent events in forensics occasionally. independence is relevant to the Collins case because I mentioned in giving you the little build-up that the math professor used the product rule. What is the product rule? Well, we may be interested in the probability that two events both happen. So far, I've only been worried about my flight delay because I'm a very self-centered person, and it's all about that. But maybe I'm interested in two different events and how they're related. And so I can ask, what's the probability my flight is delayed and my luggage is lost? So it's still all about me. Or I could ask, what's the probability I get ahead on my first coin toss and my second coin toss? That's what we do in introductory statistics classes. Or I could ask, what's the probability the Toronto Raptors win game 1 and game 2, for example, the NBA. I told you they wouldn't all be baseball, right? So basketball too. That's the basketball championship, which starts tonight. So such probabilities of more than one event can be very complicated to figure out. Okay. Why? Because if the things depend on each other, it can complicate the world, right? So if the Raptors lose game 1, they may, quote unquote, try harder in game 2 or something. So it might change the probability. It may not be right to think of the two games as just independent efforts by Toronto and Golden State. What happens in one may affect the other. The product rule, it works for that case where we have independent events. And when you have independent events, it turns out that you can just multiply probabilities. So that, for example, and I apologize, I try to avoid the simplistic coin tosses, but they're helpful here. If I said, what's the probability I get ahead on both coin tosses? I'm going to toss 1, toss 2. I know that there's a 50% chance that I'll get aheads on that first toss. So that's half the time. And half of those times, I'll get ahead on the second toss. So that's how I get my 25% that we all know is the right answer. And it turns out that it's this product rule. A half times a half is a quarter. Okay. Again, you have the advantage of not being asked to do any of this. Okay. But I do ask your indulgence as we go kind of back to the Collins case. This slide is just a total reminder of the framework we set up. So a set of probabilities were given. The expert witness said, we can multiply these together, and the prosecutor drew the conclusion that because the probability of all of those events happening in one couple was so small that they must be the people that committed the murder. Sorry, the robbery in this case. So let's return to that case and tell you what happened. They were found guilty. The couple, the Collins, were found guilty. The husband, Malcolm Collins, appealed. His wife did not. There's some interesting dynamics there. I think he had previous offenses. And they appealed on two bases: inappropriate admission of statements made while they were in custody, and they felt that the probability evidence was prejudicial to the defendant, I guess, against the defendant. Obviously, I'm no expert on admission of statements, so I will not address that part of the appeal process. But we will talk about the probability based on what we just learned. And so here's a little play at home. Was the trial court correct in admitting the probability evidence? And yes or no, and if not, why not? Talk to your neighbor for a minute or two. Let me know what you think, and then we'll talk it through. Okay, I hear people making lunch plans, which means you must be done with the exercise. So a quick show of hands before we reveal the judges, the Supreme Court of the state of California's decision. Who thinks the trial court was correct? So yes, they should have admitted the evidence. Nobody. Who thinks no, they should not have admitted the evidence? Okay. David K., you're not allowed to answer. No. Okay. You're all correct. You want to tell me why? Anyone? Brave? Jim?
Because when they were going through the subpopulation calculation of probability, they didn't do that correctly.
Yeah. Okay. So, yeah.
Well, the factors aren't independent of each other.
Very good.
Characteristics.
Very good.
Not permanent.
They're not permanent either. That's both of those statements. They talk about the same thing, exactly right. Let me walk through some of this. The Supreme Court reversed the conviction. They cited two fundamental prejudicial errors, which I've broken down into kind of 3 points that I want to talk about. Their first was they also agreed with what's been said. The testimony actually lacked adequate foundation in legal terms, was wrong statistically. But the second point is also worth talking about. They found that the testimony, and in particular the prosecutor's use of said testimony, distracted the jury from its proper role in this case. So let me elaborate on those. The first question that they asked that we did not hear here is, where did the probabilities come from in the first place? Right? The prosecution did not provide any sources. These are hard things to know. Trust me, I'm going to tell you in a second why I know that. They're hard probabilities to find, actually, but the prosecutor didn't even make any attempt at all to justify them. Okay? And the court was concerned about that, in my opinion, correctly. What the court said in its decision basically is, there needs to be some basis for doing this. It doesn't have to be the right answer, but it needs some basis. So for example, you might walk around the neighborhood and count the proportion of yellow cars, right? That would be some data that would support a probability. It wouldn't make the number right. You know, you could go to DMV maybe and find out, right? But they didn't do any of that. So it was very concerned about where the numbers came from. I mentioned here, there was a case in the United Kingdom a few years ago about shoe prints in which a similar, not the same, but a similar issue came up, and the judge there was concerned about the way the probabilities were created by the expert, and in that case more how they were applied. But so where did the numbers come from? And now I think both of you were pointing out the independence. So I wanted to, you know, I could claim they're not independent, but I wanted to try and find some data. And that's why I know it's actually really hard to find data about stuff like this. Here's what I could find. This is a survey from France, so not particularly germane to Los Angeles in 1968, but data is data. I've took their survey and distilled it down a little bit, so all men are in one of four categories here. No facial hair, mustache and beard, mustache only, beard only. And if you look at these data, you can see that the proportion of the male population with beards is actually 44%. So that's actually higher than he gave, but as I said, it's a different population. And you can also see that the proportion of males with mustaches is 47%. So now the math professor multiplied these two together, acting as if they were independent. And if you look at those two numbers and multiply them together, you actually end up with 0.44 times 0.47. I was told there would be no math in this course, but is 0.21. So if they were independent, you would expect 21% of men to have both a mustache and a beard, but we see that in fact 43% do. The way that I like to think about this is to actually turn it around. That just proves they're not independent. To understand how dependent they are, we can look at the conditional probability. And the conditional probability says, let's restrict attention from my box at the left to only those who have a beard. So that's category 2 and category 4. A total of 44% of the population. So that becomes my new population. I'm interested only in that 44%. I don't know the population of France, I apologize. But, you know, we'll call France 50 million people, and we'll say the 44% of them is therefore 22 million people or something like that. Okay, so I'm only interested in those 22 million men, not the 28 million who don't have them. Of those 22 million, it turns out that 21 million also have a mustache. And so I end up with this conditional probability of 98%. So they are not independent. In fact, they're super, super dependent. And when something like this happens, you can actually tell what's going to happen. Just this fact, if this were true in Los Angeles, would change 1 in 12 million to 1 in 6 million. So we start cutting it down so it doesn't look so, these dependencies will have the effect of cutting down that probability so it doesn't seem quite so overwhelming. So very important, independence.
Now, before you leave that slide,
Yes.
can you go back to, are these plus 01 and plus 04, are those the uncertainties actually? What's the?
No, great. Thank you for asking that, Jim. All that I did for those numbers are say, if I want to know the proportion of the population with beards, okay, I take the 43% that have a mustache and a beard and the 1% that only have a beard and add them up. So that's what I'm doing here. Your question is very important. There are actually two comments here. One is, these are based on a survey, and so there's some uncertainty associated with these. That is, as in most surveys, there's kind of a plus or minus 5%, typically, depending on the size of the survey. And so it could be as high as, 49% or as low as 39%. But that would have very little impact on the rest of what's been said here. We're going to come to your other point, by the way, too. So those were the two things that the court was concerned with that I would call, quote unquote, technical errors, right? Where did the probabilities come from? Are they independent or not? That gets to the heart of whether the 1 in 12 million is remotely the right number. But the court was probably as much, I would say probably even more concerned about the mathematics in this case being a distraction to the jury and to the lawyers. And so you can see this quote, about how misguided they believe this effort was. In particular, the court believed that this was not this kind of seemed to excuse the jury from doing the heavy lifting of figuring out whether these were the people or not. The prosecution laid it on heavily that these were the people because there's this mathematical, and used, I believe, these terms, a mathematical proof of guilt. The chances of finding another couple like this were so remote that it had to be this couple. And we'll come back to that. That's an example of a very common error that's made, known as the prosecutor's fallacy. That is looking at a probability, even if the 1 in 12 million were correct, and interpreting it the wrong way. But I'm not emphasizing that now. I'm emphasizing more here the court's concern that there was this kind of exactitude and overwhelming nature of the mathematical calculation that led the jury not to worry about things. Here you see they mentioned exactly what you mentioned, that these traits are changeable. So it's not right to assess whether the columns were the right people. Part of the thing the jury has to decide is whether there might have been a case of disguise or cars can be painted, although not in a short time frame, and so on and so forth, and whether there might be another couple. There's a fairly elaborate mathematical calculation in the appendix to this Supreme Court decision, arguing that it's quite likely there's another couple. I didn't love that part of it, but that's beyond our scope for today. Okay. So here are a few more quotes from the court, my favorite being the third one down. Mathematics, a veritable sorcerer in our computerized society. And remember, this is 1968. What would they think of our computerized society today? While assisting the trier of fact in the search for truth must not cast a spell over him. I found this really interesting. I talk about the Collins case, as I said, in introductory stat courses and otherwise. But as preparing for this, and really just for this, my previous other legal talks, I didn't quite get it as much. This part about the distraction is really interesting to look at 50 years in rearview mirror, because obviously we do this now. And so, DNA calculations are very much of this form, better justified, in fact, but very much of this form. And so that kind of evidence is relevant and when appropriate, and is now being used. So I think that's also interesting. Okay. Are we having fun? Okay. Case 2. State of Connecticut versus Skipper. Okay. The defendant in this case was charged with multiple counts of sexual assault with a child. Actually, it's a terrible case. At trial, the state's expert witness from a testing lab reported on the results of a paternity test. And the results of that test, as well as other evidence, led to a conviction. Okay? What the expert reported in the case is something that is called a paternity index. turns out, you don't know what this is yet necessarily, the paternity index is a likelihood ratio. I mentioned likelihood ratios are one way of assessing evidence. Paternity index is a likelihood ratio. So it's a ratio of two probabilities. One probability, what's the probability that the defendant would have produced a child with a given genotype, given the mother's genotype, and the second probability is the probability that a random man would produce the child, could produce a child with that genotype, given the mother's genotype. And that number was 3,500 or so. So that's one way of assessing the evidence, and we'll talk more about this. But the state's expert went one step further. The state's expert indicated that we can take that paternity index and turn it into a probability of paternity. A statement about the probability that this man was the father. And he did that. And the answer he came up with was 99.97%. So very compelling data. So I'm going to do a little bit of, again, a probability and statistics piece, and then we'll come back to that case. Now, so far from the Collins case, we know about probabilities and conditional probabilities and whether we should multiply them or not. The Skipper case raises the bar on us a little bit. The Skipper case uses more sophisticated probability calculations, and I won't go through them in great detail, but in particular, it takes those probability calculations and uses them through the likelihood ratio. So remember, I mentioned there are three approaches to analyzing evidence. You can think about the Collins case as being an example of what I call the two-stage process. Stage one was to see, I have all these characteristics from the eyewitness, and then I have these suspects, they match. And then the second stage, I should figure out how important it is that they match. What's the chance of a coincidental match? So that's what's known as the two-stage approach. This case brings us to the likelihood ratio approach, and I'm going to get to likelihood ratios, and before I do that, I need to do a little bit more probability, and in fact, even a little bit more confusing probability. So apologies in advance. Historical note, Thomas Bayes was an English mathematician, philosopher, and minister, and he's very well known in the world of statistics for his work on quote-unquote inverse probability. A word on inverse probability, my picture reproduced on the bottom here. Remember I told you probability goes one way from population sample and statistics goes the other way. What is now called statistics is something that Bayes and other, Bayes was in the 1600s, other 1600 and 1700 mathematicians called it inverse probability. That is, we're trying to go in the opposite direction, right, from the sample to the population. So we now use the term statistics for that, and in recognition of Bayes' contribution, mathematical contribution, it's the approach that I'm about to describe is known as Bayesian statistics. Interesting fact for the day. So his contribution is known as Bayes' theorem. And to talk about Bayes' theorem, it's always nice to have an example. Here's a little forensic example. So I have now two events that I'm interested in. G is the event that there's gunshot residue on a person on the suspect, say. Okay. And in this case, I'll sometimes want to refer to no gunshot residue, so I'll just say not G. Okay. And then I have a test for gunshot residue. We'll call the outcome of the test T, T for test. So T is the test is positive. The test shows gunshot residue on the person. And not T, of course, is a negative test. So everything I'm about to say you can do with home pregnancy test or drug test or whatever you like. It's common to think about these testing scenarios in a 2x2 table. This is our second 2x2 table. We're not even an hour in yet. 2x2 tables are all over statistics. So in this 2x2 table, the two rows are the truth. That's usually not known to us. That's why we do the test. Right? We don't know if the person has gunshot residue or not, but the rows are labeled by the truth. G, the person has gunshot residue. Not G, the person does not have gunshot residue. And the columns are labeled by the test outcome. T, test positive. Not T, test negative. Why some of the fonts are different, I don't know. They were not supposed to be. The four cells then correspond to the following. If the person had gunshot residue and the test was positive, we would call that a true positive. If the person did not have gunshot residue and the test was positive, that's what's known as a false positive test. And the same for the negatives on the right-hand column. These are, in fact, conditional probabilities. We love conditional probabilities. We already know that, okay? So they're expressed in the bottom here. The true positive rate is the probability that the test is positive given that the suspect does in fact have gunshot residue on their hand. That's sometimes known as the sensitivity. That is, this same language works for medical diagnostic tests, and that's called the sensitivity. And the true negative rate is known as the specificity. How specific is the test? When it says no, is it really no? Okay? So how sensitive is the test is, if it's true, will I detect it? Am I sensitive enough to detect it? And specific is, the test is specific. When it says no, it also means no. Mm-hmm. And then you have these error rates when I have false positive and false negatives. So the way these tests typically work, if you've ever done the home pregnancy test thing, is the box says, they'll give you their sensitivity and specificity based on lab tests. We know those numbers. Okay. So we know how the test works. And Bayes' theorem, he wasn't working on pregnancy tests, but Bayes' theorem is actually a mathematical result for turning the conditional probability around. Why would we want to do that? Because what matters to me as the person who may be pregnant is the test came back positive. What's the chance that I'm really positive, that I'm really pregnant? This stuff can be confusing, okay? I tried to minimize symbols, but lots of symbols and lots of confusion. Let's think about these two things. Probability of T given G, probability test is positive given person has gunshot residue. And the second one, probability of G given T. Probability person actually has gunshot residue given test is positive. Those two things are different. So that's the first thing we want to know, right? They're different. They're talking about different things. The first is talking about the probability of getting a positive test. Remember, the conditioning part just says, on what population? We're only looking at the population where people actually have gunshot residue now. But it is fundamentally about the probability that the test is positive. The second quantity that I pointed to is talking about the probability the person has gunshot residue on their hand. It is a probability that has nothing to do with the test. In fact, I already know the test was positive. That's what I'm conditioning on. That's the information I'm given. So the first is a probability about the test. The second is a probability about gunshot residue. The conditioning says which population you look at. And Bayes' theorem is a mathematical theorem that tells us how to flip it, to get from one to the other. Okay? I'm sparing you the formula, by the way. Bayes' theorem, it turns out to do this, and this is a critical point, actually. Pay attention, this comes back. Critical point. To do this, you have to know something about the prevalence of whatever it is you're testing for. If everyone in the world has gunshot residue, Wyoming, that's different than if in New York, presumably it's a smaller proportion. I won't hazard a guess. I haven't lived here for many years. So that prior prevalence turns out to matter. I will demonstrate that. But without demonstrating the formula, that matters a lot. So let's see how this works. And these are made-up examples intended to be plausible. So here's what I am assumed known. On the back of my gunshot residue test box, it says the test is sensitive. If there is gunshot residue present, if you are pregnant, there's a 98% chance that the test will come back positive. And the test is pretty specific. There are a few false positives. If you do not have gunshot residue, or if you are not pregnant, the test will come back positive only 4% of the time. So it gets it right 96% of the time there. Sounds pretty good. Test gets it right 98 on the one hand, 96 on the other. And for my first demonstration, let's assume that we are in Wyoming and that 90% of the people have gunshot residues on their hands. So unfortunately, you can't do Bayes' rule without that information. Okay, so how do we do this? The dreaded tree diagram, okay. We have 1,000, let's imagine 1,000 people, because the probability math is not fun. But we can all do this because it just requires thinking about people. Let's suppose you have 1,000 people. And I told you a few things. I told you that 90% of the people in this population in Wyoming, 1,000, that's the whole population, I think. So, have gunshot residue. So 900 of them actually have gunshot residue on their hand. 100 of them do not. The second part of the tree is let's do the test on those people. And of the 900 people who have residue, we run the test, and I told you that 98% of them, the test is going to come back positive, and 2% it's going to come back negative. Which means that 98% of 900, or 882 people, have the following characteristics. They have residue, and the test correctly identified it. 18 people have residue, but the test made an error and said they did not. On the bottom, we do the same thing for the 100 people that don't have residue. And here I told you that the test was right 96% of the time and wrong 4% of the time. So 4 of the people got a positive test even though they did not have gunshot residue. And 96%, in this case 96, of the people did not have residue and correctly got a negative test. Questions, I should have said this at the very beginning. It's a little late now that we're an hour into the show. Interrupt with questions as you like. I welcome them. Okay. At the end of the day, what Bayes did is collect the information in the right-hand column. What do I know? Now I want to look at the subpart of the population that got a positive test. How many people got a positive test? 882 plus 4. 886 got a positive test. How many of them actually had gunshot residue? 882. The other 4 were errors. So the probability of a person has gunshot residue, given that the test was positive, is very, very high. This is the way we think the world should work, 99.5%. Have a very accurate test. I got my answer back. Boom. Person has gunshot residue. We can bring that into the courtroom. Let's do example 2. Same exact calculation. I'm just going to change one number. We live in a tranquil place where gunshot residue is rare. Okay? So in this place, only 5% of the population has gunshot residue. 95% do not. Go through the same spiel. Okay? I won't bore you with the calculations. I just make that number up, by the way. It's not knowable, right? It turns out in this case, at the end of the day, there are many fewer positive tests, of course, because there are fewer people who have gunshot residue. But there are a total of 87 positive tests, only 49 of whom have gunshot residue. The probability that you actually have gunshot residue in this place, given that the test came back positive, is 56%. There's this large number of people going through the no gunshot residue, and some of them come back as false positives. When people talk about drug testing everyone, this is what we worry about. There's a small probability that people are using drugs, maybe, hopefully. And when you do the Bayes rule calculation for the drug test, you end up with a reasonably high proportion of false positives. And there are debates about breast cancer exams, how often you should have them. Same exact issue. If you do exams on everyone, you have a low-risk population, right? The debate is around young women. They have a lower probability, and so they have more false positives. And so there's a cost to doing that, both a monetary cost, but a cost on people's lives. And there's no obvious answer what the right trade-off is. Okay. So that's why Bayes' theorem is important. It allows us to kind of do this calculation, this quote-unquote reversing the conditioning. So I'm of a Ghostbusters era, right? Don't cross the beams. Here we're kind of crossing the beams, right? That is, we have information about the test given the true state of the world, but we're much more interested in the true state of the world given the test. Okay. So what does this have to do with forensics? Okay. So here's a framework that will take us through most of the rest of my remarks today, both now and in the afternoon. I should have said that. The same set of slides kind of carry on into the afternoon. I have a possible breaking point. We'll see if I get there or not. The E in this case is evidence, just as a generic placeholder. It could be 2 DNA profiles. It could be 2 sets of measurements on glass fragments, fragments found at the scene of the crime, fragments found on a suspect. So lots of examples. And there are 2 hypotheses. The hypotheses here are in some respects playing the role of test. No, sorry, I said that wrong. The hypotheses here are playing the role of the true state of the world. Okay. Like, does the person have gunshot residue or not? In this case, the 2 states of the world that I want to talk about are what's labeled here H with a little s, which is the same source view of the world. These 2 sets of measurements I have came from the same source. The glass at the crime scene and the glass on the person's jacket are from the same window. Okay? H sub D is the different source proposition. The 2 samples have different sources. This guy has glass on his window because he was working on his house this morning. Right? 2 different pieces of glass. Okay? And then you can see how I can kind of put this in the framework we just talked about for the test and the gunshot residue. We can talk about first the probability of the evidence, the test, given the true state of the world. How likely is it that I would see evidence like this if the suspect is the source? And the second, how likely is it that I would see evidence like this if it were not the source? If the suspect were not the source, if they were not from the same source. So it turns out that's something we can often say something about, just as we could in the gunshot residue. We may be able to say something about the probability of the evidence given the true state of the world. We knew, the drug companies that develop pregnancy tests do experiments with samples where they know the answer, and that's why they can tell you the probability the test will come back positive if you are pregnant. In this case, there's scientific knowledge often that allows us to say, if in fact these 2 samples came from the same source, I know how similar I would expect their glass measurements to be. I know I would expect their DNA profiles to match exactly. So there's stuff that we can figure out for those 2. But what do we want to know in the classroom, in the courtroom, and the classroom? We actually want to know the opposite, the flip. Right? We want to know, I've seen the evidence. Can you tell me now about the probability of these 2 hypotheses? So this is why what we just went through is relevant to us. We can do one version of the probability, and we want to flip it if we could. Okay? But remember, flipping was hard. It required some information about the population. So a little bit about the likelihood ratio, and then we'll return to the Skipper case. The likelihood ratio, as I said before, is getting a lot of attention. It's a statistical concept. And there are some people, and I would probably count myself among them, who believe that it provides a single unifying logic for thinking about forensic evidence, that everything kind of could fit in there, not everything. The likelihood ratio, I want to point out, is not specific to forensics at all. It was not developed for forensics. It doesn't care if forensics uses it or not. Okay? It has a very nice business on the side on its own already. Okay? It's used in statistics to generate all kinds of tests, and it is used with medical diagnostic tests. Europe loves the likelihood ratio. I can't tell you why. They just do. I'll tell you more about it later. But they've kind of agreed with the statement that I made, that they think the likelihood ratio is the right way to do this. More on that later. So here's the formula. This is one way of writing Bayes' theorem, the mathematical theorem. It turns out to be super, super important for the ongoing discussions about the likelihood ratio, and it turns out to be super, super important for the Skipper case that we're talking about. So again, E is evidence, H sub S, same source, H sub D, D source. I'm not going to prove this. This is just true. I like to say that is just true. This part is not up for debate. Mathematically true, okay? Sometimes people say, I don't know if I want to use the likelihood ratio. You don't have to use the likelihood ratio, but this is mathematically true. And what it says is The piece in the middle is what's known as the likelihood ratio. It is a ratio of two probabilities, quote unquote, two likelihoods. Right? A probability is the likelihood of an event happening. So one is the probability that I would see evidence like this if the two evidence samples come from the same source, and the denominator, what's the probability I would see evidence like this if it has different source. And so, if you think about fingerprints, what's going on? The evidence is the latent print and the known print. The evidence is I look at them and I say, oh my God, they agree on this bifurcation, they agree on this ridge ending. This has a ridge ending here that this doesn't, but gee, it's kind of blurry there, so maybe it's there and I'm just not seeing it. That's the evidence. So that's a little fuzzy evidence, but that's evidence, right? And I say, how likely, the examiner say, how likely is it that I'd see these matching features and these few dissimilarities that are in the smudged area if it was the same source? How likely would I see this much matching in these smudges if it were a different source? That's the likelihood ratio. What Bayes' theorem tells us how to do is take those probabilities and turn them into what I think we all agree the jury wants to know, which is, given this evidence, what's the probability that the suspect was the source of the evidence? And it's expressed here as a ratio. What's the odds that the suspect was the source of the evidence? The ratio of two probabilities are the odds. So this is the odds that it's the same person divided by over relative, the odds that it's the same person rather than a different person. And what Bayes' theorem tells us, what we saw in the simple examples, was to flip the probability around, to turn the conditional around, you need some information about the true state of the world. You need to know beforehand, sometimes in mathematics we say a priori, before looking at the evidence, how likely is it that it's the same source? How likely is it that it's a different source? So Bayes' theorem is a way of taking prior information. You can think about guilt and innocence. We're really only talking about one piece of evidence here. But prior information about the same source versus different source, updating it with the information I see, the evidence. This is the good part. We actually have data about this. Okay? And that allows you to speak about the posterior probability, with this, what's known as the a posteriori probability, after looking at the evidence. Okay. There's actually a lot of subtlety here. So I know that lawyers like fine print and footnotes, so this is my fine print and footnotes. But there's a lot that you could talk about here that we're not going to talk about today, including something that somehow confuses a lot of people, even in the statistics world, which is calling it a likelihood ratio or calling it a Bayes factor. For us today, they're the same thing. Okay. So again, I already said this, likelihood ratio is an attempt to generate a quantitative summary of the strength of the evidence by comparing two probabilities. How likely the evidence is if the same source, how likely the evidence is if it's a different source. Okay, so as we've talked about, there's a lot of room for confusion here, so let me tell you a couple of common confusions that arise. We'll start with an example. So let's think about DNA because it generates big numbers. Suppose I determine that the probability that the two profiles match at random, that is, the suspect is not actually the source of the DNA sample at the crime scene. The suspect is innocent, they were nowhere near it. What's the probability that they would show up with a matching DNA profile? Turns out to be 1 in a million in this case, because I made it up, so I know it. Okay. So that's the probability of the evidence given a specific hypothesis, in this case, that it was not the suspect. The prosecutor's fallacy, which is a term I introduced earlier in talking about the Collins case, is to look at that and say, wow, the chances of getting evidence like this, if the person was innocent, is 1 in a million. And reading that as saying, the probability that this person is innocent is 1 in a million. Those are not the same thing. The first is a statement about the evidence. The second is a statement about the hypothesis. So that's why it's called a fallacy, obviously. So if you do that, then you are led to, as the prosecutor did in the Collins case, say, wow, these really low numbers mean I must be guilty because the chances they're innocent are so low. But that is not what the data say. The data are telling you about how likely you are to get the evidence under one particular hypothesis, but as we saw, we want to compare two hypotheses. So we know we can't get that answer that the prosecutor wants by just looking at that number. There's a corresponding, I guess, since everything is fair play in our adversarial system, there's a corresponding idea that's known as the defense attorney's fallacy. There are at least, in this case, 1 in a million, and a population in the US more than 300 million. There are at least 300 such people in the US. So the evidence is not helpful, because, yeah, me, the defense attorney, the suspect matches this, but gee, there are 300 other people. So, who cares? Not that unusual an event. Right? So both of those are wrong, in part because you need to look at the two hypotheses to judge them, how much they tell you about the evidence. So how do you describe the likelihood ratio? This is how I describe it. It may or may not be helpful in court. The evidence in this case, if the person is the suspect, we assume the probability they'll match is 1, certainty. That's not true, but we'll act as if it is. If they're not the person, I told you the probability the evidence would match is 1 in a million. The likelihood ratio is the ratio of those two numbers, 1 divided by 1 in a million. And the answer turns out to be 1 million. Okay? And then I would say the evidence that we see in this case, ladies and gentlemen of the jury, is 1 million times more likely if the suspect is the source of the evidence than if a random other person is the source of the evidence. That should sound familiar, because in the Skipper case, that's what the paternity index said, right? I compared the probability that the suspect was the father to the probability that a random man was the father, and I came up with a number. I'm going to say a little bit about this probably later this afternoon. You probably can vouch for this. This stuff is hard to understand, and if this group of highly educated people has trouble understanding it, what's a jury going to do with this stuff? Interesting question. Okay. I mentioned the Europeans like likelihood ratios very much. They've endorsed this as the appropriate way to report evidence. They recognize that the numbers are tricky for people, and so they created a verbal equivalent scale. If the likelihood ratio is really large, like at the bottom, you can either give the likelihood ratio, that is their preference, that you would give the likelihood ratio. But if you don't want to give the likelihood ratio, you can say the evidence provides extremely strong support for the same source proposition relative to the different source proposition. And so there's a verbal scale. They found that these are less precise, obviously, than the numbers, but maybe easier for people to understand. This is so important that it appears like on 12 slides. Okay. So, we don't want to cross the beams. The probability of the evidence given the same source hypothesis is not the same as the probability of the same source hypothesis. And in words, thinking about the Skipper case, the probability of getting the evidence given that the suspect was in fact the father is not the same as the probability that the suspect was the father given the evidence. The probabilities of different things. One is probability of evidence, probability of a specific profile. The other is probability of a hypothesis of a specific state of the world. They have to be different. And the last bullet, the last two bullets here, the last two items say, remember, to turn it around in this way, we must have what I could hear pre-evidence. Before looking at the evidence, if I'm going to give you this posterior probability, I must have had an a priori opinion about the same source. And there's an open question about whether we want our forensic experts to form such opinions before they look at the data. Most people, I don't think, believe they should. How are we doing? Okay, so I'm going to quickly run through the, yes?
It is, so how are we going to get to the way of convincing a layperson, a juror, as to whether these things actually represent the truth of the world, as you just said? So isn't this just fancier wording about the guy back in 1968 in some ways? If it's not the truth, I mean?
The argument goes, the argument I make goes, the likelihood ratio is a summary of the evidence. And it gets onto this scale that the jury's kind of managing within their brains, right? I have to decide which hypothesis is true. It is appropriate for the jury to have some opinion once we get to this point in the trial. They've heard a lot of stuff already, right? The evidence now comes in. They've heard stuff. They have some prior opinion or not. Then an expert sits down and says, you know what? This glass evidence is much more likely if the suspect was at the scene of the crime than if not. That is, to my mind, statements of fact, not so, but there's evidence there. There's a mathematical summary of the evidence there. I made certain calculations and I got this answer. I'll come back to that. But so the argument that I'm making is that part is reasonably, can be reasonably shared as the expert's view of the strength of the evidence. And then the jury gets to update that. I worry about, and what this says is, I worry about the expert saying, based on my analysis, I'm 99% sure that the suspect was at the scene of the crime. Because for the expert to do that, they must have had a prior opinion that, in my view, they're not entitled to. Okay. I'm not sure I completely addressed your question.
So why should it be in court?
Well, the likely ratio, I would argue the likely ratio should be in court because that's the summary of the evidence. So that's the piece that should inform the decision maker. The second bullet here is if the forensic expert is testifying about the second quantity, they are usurping that responsibility from the decision maker. They are opining about the hypothesis. They should opine only about the evidence, in my view. Question?
In a case like that, what would happen is that the appropriate thing would be for the defense attorney or the opposing counsel, once presented with the discovery that they intend to use this evidence to challenge it vis-a-vis motion, and that there would be a hearing before the trier of fact, who would then determine whether or not it doesn't offend one of the rules of evidence in terms of bringing it in, whether or not its probative value outweighed by its open prejudicial value, or that it would just confuse the trier of fact. That's usually what happens. So you know, by the time you get to the point where you're at trial and using it, you would have lost that particular motion hearing, and then you would have formulated some counter, which is usually the flip side of the statistical argument that the individual makes. And you get up there and you intelligently cross-examine them that, okay, you said such and such, however, X, Y, Z is also true. Is that not correct? And they'll have to say yes, etc. So now you've given the trier of fact the two sides of the scale.
So obviously that's a critical part of what we do, but what I'm talking about, sorry, I didn't mean but, that's a critical part of what we do. I try not to say but. It's a critical part of what we do. The discussion we're having now somehow is a teeny bit different than that, which is take something like fingerprint evidence, which is very well accepted. So you're not going to challenge fingerprint evidence. I mean, you might, but it's probably coming in under current interpretations, okay? The discussion I want to have is there's a committee right now that's working on what standards should we make for fingerprint examiners testifying about fingerprint evidence. And I want my points to inform that, and I want you to be aware of that so that when you cross-examine, you can kind of say, wait, didn't your committee say that you shouldn't make this statement about posterior probabilities, that you should only make this other statement? So you're correct, that is that it plays out often the way you described it, but we're talking about here at a different level of the discussion, even once the evidence has been admitted, about what that exchange might look like. And we'll talk a lot more about that in the afternoon, so I'm going to put it aside for now. Okay. Great questions. Yes, Sarah.
You mentioned previously that in Europe, that Bayes is used all the time. Do they use the comprise as well, or do they just?
No, well, thank you. The question is, what happens in Europe with respect to this potential source of confusion about probability of evidence versus probability of hypothesis. The nice thing, the Europeans are very clear on this. That is, they are supporting the likelihood ratio, the probability of making statements about the evidence as the way to summarize the evidence for the trier of fact. to add to their scales and make their decision. So they're on the side I am in terms of likely ratio. Sometime later this afternoon, we'll talk a little bit more about what the Europeans say. There are some things they do that I don't necessarily like very much, right? The question is, where does this likely ratio come from? I haven't said much about that yet. I was about to, but questions are good. Yeah?
Without a verbal scale, what's another way to describe the likelihood ratio?
Great question, great question. So, you didn't like mine? Sorry. Nobody knows the answer to that. We're struggling for that. One idea that people have floated is an idea of saying, how strong is this evidence? Well, 1 million is as if I got heads 20 times in a row. Right? You know, that your surprise at this evidence should be about the same as your surprise if I got 20 heads in a row. So that's one idea people have thrown out. But it is not obvious how this should be. And anyway, a little bit more on that later, too. Yes?
Do you have time to discuss the Monty Hall probability?
No. At lunch or otherwise. Okay. Great questions. I think most valuable is that we go to the Skipper case and kind of wrap that. And then I'll come back in the afternoon and talk a little bit more about likely ratios and then some of the issues we were just discussing. So I'm going to just go through a few slides about how it works in DNA. But I think it's important to wrap the case. So we return to the Skipper case. And again, these are the things I told you before. Okay, the expert reported a paternity index, which is likely ratio, and then said, I can turn this likely ratio into a probability of paternity. And you now have the mathematical background for doing that. But Bayes' theorem was the way that we could take a likelihood ratio, multiply some prior odds, and turn it into a posterior. Okay. So here's what happened in the case. The defendant was convicted, based in part on the testimony of the expert. There was an appeal in this case on several issues. Again, two were totally outside my lane, so I stay out of them. One in my lane, they filed an appeal that the statistical evidence associated with the paternity test was improperly admitted. And again, was the trial court correct in admitting the probability of evidence? If not, why not? So take a minute, talk to your neighbor. Again, the evidence was this probability of paternity is 99.97%. Person's found guilty. Defendant appeals, saying the statistical evidence was improperly admitted. What do you think? All right, I'm going to call us back quickly. I apologize, but I value your break and my break too much to go on too long. So how many people think the probability of evidence was done correctly? A small number. How many think it was not? Mm-hmm. Still a small number, a bigger number, but a small number. I hate to ask the third option. How many people have no idea what we're talking about? Okay. Anybody want to explain their no? No. Anybody want to explain their yes?
No, I'm stupid, so I said yes in this case because it looks like the prior probabilities were investigated by the company that actually did produce the test.
So that's the key issue. I disagree on the substance, but it's the key issue, which is, the prior probabilities, right? And in this case, the expert from the company made a choice. And the state found the application of Bayes' theorem in this case was inconsistent with the presumption of innocence. Why did they say that? The court determined, interestingly enough, the expert was not explicit about what they had done. But the court determined that they had used a 50% prior probability of paternity, and therefore a 50% prior probability of not being the father. And so the prior odds were 1. Okay? And the court says, it's antithetical to our criminal justice system to presume anything but innocence at the outset of the trial. So assuming that the probability was 50% that he was the father, assumed he was guilty, that he had committed the sexual assault. There are several pieces here. And in the end, the court said, we can't say this didn't influence the jury, so remanded for a new trial. Okay. This slide you've seen before. The paternity index is the likelihood ratio. So that was 3.496. And as the Supreme Court correctly intuited, the expert had put in a prior odds of 1 to 1. So the right-hand side was 1 over 1. The middle was 3496. You multiply them together, that's an easy one. You get 3496 on the left. So the posterior, they're called the posterior odds, and then the expert turned that into a probability, which is very easy to do, and ended up with 99.97%. So if you start with 50% prior probability, the data changes that to 99.97%. As we saw with the gunshot residue test, if you change the first, you can see what would happen to the last. And so that's sometimes people say one way to do this is to provide the jury with a table. If your prior opinion was this, and I showed you this likelihood ratio, your posterior probability should now be this. That doesn't happen. David Kay will tell us why later. But that would be one way to think about this is, right, to get a posterior probability, which we kind of all agree the jury needs to form, we could give them a table that says, if you were here before the evidence, this is where you should be after the evidence. But not everyone likes that idea. So that's what happened in this case. That's what this slide says. That's exactly what happened in this case. But we talked about this before. The odds here are critical. The difference between these are critical because it requires the prior odds. Okay? And the court was very concerned about that use and found that inconsistent with the presumption of innocence. Now, there's something interesting about this. I think it's on the next slide. Nope. Good place to break is on the next slide, but we're not there yet. There's something interesting about this, which I did not put on the slide, but is in the decision, which is the court recognized that this logic fails at some point, which is any presumed prior probability that the suspect is the father, 1%, 2%, right? In making that presumption, you're allowing for some prior probability that this person committed the crime. And therefore, if you didn't make that such a presumption, you'd have 0 prior probability, and no evidence would change that. And so there's some piece of logic here that doesn't quite work in the court's reasoning. I actually agree with the decision they reached about 50% probably not being right, or it needs at least to be much more explicit. I would say we shouldn't do it. I'd stop at the likelihood ratio, which is where the court wants to stop, because the likelihood ratio is considering the 2 possible states of the world, but it's not attempting to assign a probability. So it is 10 o'clock. I skipped a few slides, which I'll add into the afternoon piece, but this is a good time to break. I thank you for your questions and your attention. I'm going to pick up pretty much where I stopped in the morning. So if you're new here, apologies. I will try to bring you up to speed. But we discussed 2 cases in the morning. So a little bit of a review/preview. I mentioned at the start that there were three ways in which forensic evidence gets analyzed and interpreted. One of those is as expert opinion, and we heard the firearm examiner really talk about that. That's what they do in firearm analysis. The second is in some kind of two-stage process where we see if there's a match, and then we try to assess the probative value of the match. And the Collins case was an example of that. Much of what happens in DNA can be thought of in that way. We see if there's a match, and then we get a number that says how significant or how important that match might be, how probative that match might be. And then the third approach is the likelihood ratio, which I talked about in terms of a particular case. I'm going to go back there to mention one point that I think led to a lot of the questions, a place where I was not as clear as I might have been. I won't say a lot about it because I know that David Kay, we've talked, and he's going to come back and talk about it in the paternity context again. But you may remember this slide. This is the Bayes theorem written in a form that it is most commonly written in to apply to forensic evidence, in which the likelihood ratio is the piece in the middle, looking at the probability of the evidence. And I mentioned that to get the left-hand side, the posterior odds of the hypotheses, you multiply by prior odds. And so that's a famous formula. What maybe didn't come across as clear is what I've been advocating, what people who like the likelihood ratio advocate, is basically that what is the role of the forensic examiner? The forensic examiner is to analyze the evidence. And so that if all goes well and we provide the right tools, the right mathematical or quantitative tools, that would speak to the middle term. They could make statements about the evidence. How likely is the evidence if this suspect was the source? How likely is the evidence if another random person was the source? And that would be where the forensic examiner would exit the scene. And the notion is both the prior odds and the posterior odds are the domain of the trier of fact, the judge, the jury, to kind of look at based on other evidence that may have come up in the case up to this point. They would take the evidence from the examiner and then update. So I won't say more about it, but I apologize if that was not clear earlier today. That's old. What I wanted to do, I said I was going to do a recap and a look forward. So the things we've looked at so far have been about the likelihood ratio in the two-stage. So I have a couple more cases to discuss, and they relate to expert opinion, and I think make a nice complement to the bullet discussion that we had and some of the questions that were raised, and so maybe can continue that discussion. Before I do that, though, I think the likelihood ratio is important and interesting, and I think a lot of the ongoing discussion is about it. And so I wanted to try and elaborate a little bit on the likelihood ratio in terms of, so what exactly do we mean and how might it work in some of the more complicated forms of evidence? And so it's easiest to start with a place where likelihood ratio we know works because it's used. And so I set up a very simple scenario here in which there's a crime scene sample, and I have in parentheses known to be from a single source, since the people who are familiar with DNA will know that mixtures of DNA, samples that contain multiple individual contributors, are more complicated, and I don't want that for now. And then we have a sample from the suspect, and it turns out their DNA profile matches. And so a DNA profile, if you have not seen one before, is something like what you see at the left. There's some data that goes before it gets to this point. That is, someone has to analyze the basic data and what's called the genotype, the alleles. And so there's a bunch of markers here, I think 16 or 17, and the first row identifies a marker, a spot along the genome, and at that spot, this particular person has two alleles, one is a 20 and one is a 24. They get one from mom and one from dad. And then you go to the second marker and they have these other alleles. What the alleles are is not so important, other than that there's a small alphabet of alleles that are possible at each location. The evidence E in this case is the two matching profiles. And the numerator is the probability of observing matching profiles if there is a single source, which for the moment we'll just take to be 1, approximately is. And so the interest in the likelihood ratio in this case turns out to be how do you calculate the denominator, the probability of observing matching profiles if in fact they came from different sources. And the way that works is we understand the biology and we have data. And so I've circled one of the markers, TH01, for which this individual has a 7 and a 9. And we ask the question, how likely is it that a random person would match this 7-9 sample. And you can determine that because we have a table here of each allele and how often it occurs in the population. And so to get a 7 and a 9, you have a 16% chance of inheriting a 7 and a roughly 20% chance of inheriting a 9. And they get multiplied, and they get multiplied by 2, because you don't know which one came from mom and dad. So you could have got a 7 from mom and a 9 from dad, or vice versa. And if you do that multiplication, you find out that that probability is 0.06. And the likelihood ratio wants 1 over 0.06. And so that ends up being 15 or 16. So what's the big deal about DNA, right? That's not huge likelihood ratio. Well, that's just one marker. And so if you have more markers and they're independent, as we discussed this morning, you get to multiply probabilities. And multiplying probabilities in this case turns out to be the same thing as multiplying likelihood ratios. And so the original CODIS system that was in use had 13 markers. So you take a number like 15 from each and multiply it together 13 times, that's a pretty big number. And now they do 20, so that's an even bigger number. Right? So they're not all 15, some are 5, some are 10, whatever. But you end up with very, very large likelihood ratios, obviously. So we talk about this case because it works well, and it points out what you need to do the likelihood ratio, which is helpful for a lot of the ongoing discussion about, hey, can we quantify firearms evidence or not? How might we do that? So here are the key points that I always think about when I look at the DNA case. It works because we know the biology. We know how we inherit our genes from our mom and our dad. And that biology gives us a theory for probabilities. And we have databases that tell us how likely each allele is. And there's been a large peer-reviewed literature. So the likelihood ratio in DNA works very well, although, as we've talked about, mixtures are challenging still to this day. And there are other contamination and other issues as well. So no evidence is perfect. But DNA is a place where at least we know how the likelihood ratio works. Skip that because we already did the skipper case. Good, was a very nice break. Okay, now we're back. We've already done this review. I thought I would kind of finish discussing the likelihood ratio by talking a little bit about likelihood ratios for pattern evidence. As I mentioned, that's kind of the thing that CSAFE, my center, is involved in, and therefore something I've been spending a lot of time on. Lots of things are called pattern evidence, but they're basically when a pattern or an impression is left at the crime scene, we call that pattern evidence. And so that includes latent prints, which we heard a little bit about with the new technology. It includes shoe prints, which you see a picture here of a known shoe on the left and a print at a crime scene on the right. It also can include questioned documents, signatures and things like that, and firearms and tool marks, again, which we heard about. So the likelihood ratio here is what we're aiming for, but it's very, very hard. So I wanted to say a little bit about why it's so hard. You can, if you wish, kind of contrast with the DNA story that we were able to tell. The starting point is the data is very different. The data in this case really is something like this. We have 2 images. So images are typically tens or hundreds of thousands of pixels, basically. And that's all you have to start with. Okay. So the data is very high dimensional. And there's a lot of flexibility in defining what features to look at. So most people are familiar with what we mean by features in fingerprints. We have matching minutiae, meaning ridge endings or ridges coming together. And so those are the kinds of things. In ballistics, as I mentioned in my update about CSAFE, people look at things like matching stria as a feature. But if your starting point is an image, there's an untold amount of data here that you could call upon. And so how do you do it and how do you collect data about it? Those are the hard things. So for now, I'm just going to take E to be kind of fuzzier than as a statistician I'm comfortable. I like when E is numbers. I know what to do with numbers. But E in this case is I have these 2 images, and I have some ideas about similarities and differences I see in these 2 images. So that's the first step. Now to draw some conclusion, I feel like I'm missing a slide, but it's not there. So there's not there, it's not there, right? There's nothing you can do. Okay. Suppose I was going to talk about trace evidence like glass in between, but we won't. That's why there's a reference to trace evidence here. But to understand likelihood ratios for pattern evidence, we need to understand kind of two things. One of which is information about how much variation you would expect if you had two images from the same source. Because that's one of the hypotheses, is that these two prints, typically one is relatively pristine because it was taken from the suspect, one from the crime scene, which is kind of messy typically. Right? But so under the hypothesis that they came from the same original finger, I need to understand how much variation I should allow. There won't be a perfect match. How much should I allow? And then I also need to have some information about how much variation you'll see in features from different fingers. And there's a lot of differences you might see, of course, but characterizing that is complicated. And even more complicated in some of these cases, like shoe print, you have to know something about manufacturing, distribution, wear, to understand how common some features might be. So to do a likelihood ratio for pattern evidence, we would want to measure how likely am I to get the evidence, these similarities and differences, if it's the same source, and how likely if they're not. And so this is really, really hard. That's what people are working on. So I'm going to describe three approaches. But before I do that, I want to say a teeny bit more about why it's so hard, and why math, especially thinking about it as a statistician. I read a paper once, okay, in which it's written by an academic, so I'm not impugning any examiners or anything. This was written by an academic researcher. And he said, I'd like to demonstrate how the likelihood ratio could work for handwriting. So he had two signatures. It was his own name. He just wrote his own name. And he said, here's how it would work. I would look at these two signatures, and I see certain similarities and certain differences. No, none of us are machines. We have slight variation when we sign our name again and again. And he said, and I look at these two, and I say, what's the probability that I would see this much similarity and this kinds of differences if there were two signatures by the same person? And he said, I'm assuming that's 90%. So now, we haven't spent a lot of time talking about probability, but I encourage you to think about it. Where's the other 10% going? How do you assign probability to something as amorphous as this? The other 10% is what? Signature looks like this, but has a few more dissimilarities. That gets 1%, has a lot more, that gets 2%. It's impossible to put, we put probability distributions live always on numbers because we can do that. We know how many alleles are possible, and we can figure out which ones come more frequently. We can assign numbers to them, so we know how likely certain evidence are. In this case, you can't assign evidence to images, probabilities to images. The space of possible images is huge, right? Every pixel in that image could be dark gray, light gray, black, white. And there's tens of thousands of those. Right? So there's, the number of images is, so you can't assign probability to images. So what do we assign probability to? That's why it's so hard, that the likelihood ratio for pattern evidence as it's framed is virtually impossible. So what are people doing, since people don't take impossible for an answer? It's part of what defines us as Americans. We don't take impossible. So there are three approaches that I want to describe. One you've already seen, which is one way to do this is to reduce the image to a smaller set of features where you might possibly be able to assign numbers to them. And so this is from a paper by a fellow named Cedric Newman, who's done a ton of work on fingerprints. And here's one of his ideas that he's published. I'm not sure Cedric believes that this is ultimately going to yield success, but it was a step along the way. So what he did is he said, let's focus in on some of the minutia. And so these red arrow type things are minutia from the print. And he gave them a mathematical representation. So that's what's happening in B, C, D, and E, is each feature got three numbers assigned to it. One, which is the angle at which it sits. Another of which is the type of minutia it is. Is it a ridge ending or not? So that's not a number, but it's a small number of possibilities. And the third was some measure of size of this triangle that co-located the minutiae. So there's a lot of work that's going on here. Okay? But the end result of that work is to try and address this problem I put my finger on by saying, okay, this fingerprint is hard to think about probability, but let's replace it by, there's 7 minutiae, so he's replaced it by, in his approach, 21 numbers. That print replaced by 21 characteristics. The 7 minutiae, the angle, type, and size, quote unquote, of each of these minutiae. So that's not enough for you to do it. It's not enough for me to do it. I don't know how to do it, but that's how Cedric did it. Once you have the numbers, though, you can begin to say, what is the distribution of different minutiae types? What is the different distribution of these triangle sizes across different prints from the same person and across different people? Still very hard, right? There's an enormous data collection. I spoke this morning about the challenge. You don't have a database of multiple prints from the same person repeated for many different people. If you had such a database, you begin to say, oh, I could fill in some of these probability distributions, but it's really hard. So that's all I'm going to say about it. Really hard problem. There are people thinking about it, but most of the progress that's being made is not being made in that way. So what else might one do? One might use what some people call subjective likelihood ratios. And another approach are score-based likelihood ratios. So I'm going to say a little bit more about those last two. I guess only one of them. No. The subjective likelihood ratios, I kind of already showed you a little bit of what I would want to say, which is we had a slide about the European standards that have been written, the European guidelines, not standards, guidelines that have been written. And the European guidelines say the likelihood ratio is clearly the right way to summarize forensic evidence. Ideally, that summary will be informed by data collected. But if not, it's okay for the examiner to assign a likelihood ratio based on their experience. So they believe so strongly in the likelihood ratio that they say that's the right framework. But if we don't have data to fill in those probabilities, that's okay. That's where we'll take the expert opinion. So it's okay in Europe for an expert to say, I've looked at this fingerprint, I see this many matching features, I see a couple of discrepancies, but they all appear in, the fingerprint was in a bloody mess, and the discrepancies appear there, so they're kind of easily explained away. I consider this 1,000. Most folks in the US get a little queasy about that, including me. Where do these numbers come from, and where does validation come from, and so on and so forth, if you do that. But the Europeans have made their peace with it. That is, they believe so strongly in front of the likelihood ratio that they have really changed the problem to how do we best inform the creation of a likelihood ratio. And so they're looking at techniques to inform that. The thing that's happening more often in the States are ideas based on scores. And I don't know if anyone, have people in the room heard of FR stats, which is a fingerprint? So, all right, FR stats is coming up. So the score-based idea is the following. Evidence E is complicated. I argue that you can't put probability on the space of signatures. It doesn't, I don't understand what it means. So one approach to avoiding that is to replace the evidence by a single score that takes the two images and says similar or not. And then once you have that score, you have a much simpler problem. Not a simple problem, by the way, a much simpler problem, but still very hard. And what might that look like? So I'm going to show you two things. The first is what I would call a score-based likelihood ratio. And the picture to look at is this one over here on the bottom right. This is the distribution of scores for two different kinds of exemplars. The black curve, so here my similarity score is actually a difference score. Large values of the score mean not similar images. Small values of the score mean similar images. The black is derived by looking at a set of instances in which I know the two images came from the same source. And I compute the score for each pair, and I have this black curve, which shows the distribution. Most of those scores are between 0 and 20. There are some still out here, 20 to 40, very rare out to 60, and almost never 80 or 100. I made up this data. So that's the black curve. The red curve are known non-matches. Known non-matches we would expect to be less similar, more different. And so the red curve, it was originally dashed, but that was a little hard to read, so I sketched in a red curve over it, is more likely to be 20, 40, 60, 80, 100, or something like that. So you have these two distributions, one of which is the distribution of scores from known matches. The other is the distribution of scores from known non-matches. Remember, that's what we wanted. We want, what's the probability of seeing the evidence if it's the same source? What's the probability of seeing the evidence if it's a different source? And one way to use that here is, suppose now I have a case. The case, I take the two images from the case, and I compute my score. It's S, right here. The relative height of these two curves basically gives me my likelihood ratio. The black curve says, this is how likely it is to get a score like that from matching pairs. The red height, this is how likely it is to get a matching score from non-matching pairs. The ratio is the likelihood ratio, what would be called a score-based likelihood ratio. So you can do that. In this case, you know, it looks like it's around 5-1 or something like that. And so that would be one way of summarizing the evidence here. But as I said, this is simpler. You can see how it might work, but this is very challenging. Why is it challenging? The score could depend on lots of things, and we don't even know all of them. Let's take fingerprints. The score may, for example, depend on the number of minutiae. So I said I would talk about FR stats. This is from the peer-reviewed journal article that provides the description and argument for FR stats. Henry Swafford, who developed it, has a score. In this case, his score is a similarity score, so I apologize for that, a little bit of a switch of the sequence here. High scores mean better match. Low scores mean worse match in this picture. And to use it, he realized that you need to think about it separately depending on the number of minutiae. Because why? At the bottom one, if you had 15 minutiae, notice that the matching pairs in the light color have scores around 50 to 75. The dark non-matching pairs have scores around negative 75. And there's almost no overlap. Go to the opposite end, look at the 5. Suppose you only have 5 minutiae. The known matches actually look kind of similar. They're a little bit smaller, but they're basically the same. But what's happened is with 5, the probability of getting a coincidental match has increased. And so it's not unusual with just 5 minutiae to have non-matching pairs show up with good scores. I'm not sure how clear it is, but you can see that there's actually a big hump inside the known match that belongs to the non-match. So there's a chunk of overlap here. So this was really good that Henry did this, because it's a critical factor to interpret the evidence. You need to know the number of minutiae. I've talked with Henry many times about this. The issue that is challenging for people who develop score-based likelihood ratios is, this is great. We knew this was going to be an important factor, and it is. Are there other factors that we haven't looked at yet? Does the actual physical size of the latent print matter? Does the substrate that was used to develop it matter? There are reasons to believe the answer to some of these questions are no, but kind of the science in it would say, let's check that. And a little anecdote, not meant to belittle anyone. I and a colleague were called in to meet with Henry about FR stats. And he worked at the Defense Forensic Science Center in Atlanta, Georgia. They do forensic support for the DOD. And they wanted us to kind of bless it and say, this is great, you should use this. And I said, you know, it's really good. We gave him some feedback, which he was happy to get, about ways of improving his scores and things like that. We had a really wonderful day and a half there. And at the end of the day, I said, you know, to be honest, I really like it. It's the direction I think the field ought to be moving, but I'm not prepared to bless it, in part because I'm not a fingerprint expert, and I don't know what factors you should be looking at. You looked at number minutia, that's great, but the attitude was, we've done enough, right? And I said, that's not me to say. You need people who are fingerprint experts to say that, and you're the fingerprint experts. So, the way science typically works in the university setting is the people who are doing the experiments are their own worst critics. They say, I'm about to submit this paper. What is a referee going to look at? And then they try and address that in advance to the degree possible. So they would say, I wonder if the size of the print matters, because somebody's going to bring that up. Let me test that. I wonder if the substrate matters, it was in blood or it was on I should test that. And they really hadn't done that work. And so ultimately I spoke with Henry's supervisor and I had a couple of back and forth. And we reached an agreement that, this is for them to determine. They should do some more experimentation. And they had started to use it, not exclusively. It's in concert with their expert opinion approach. So this has some real potential. And in fact, the ballistic approach that CSAFE is developing, that I showed you before lunch, looks a little bit like this. It ends up with a score, which is the probability that you're a match or not. And that's what they propose to use. So score-based approaches seem very promising. So there are a couple of last things to know about likelihood ratios before we leave them goodbye. One, and again, people may know this because it got a fair bit of publicity, two NIST scientists, Steve Lund and Harry Eyert, both statisticians, wrote a paper in a NIST journal that pointed out, one of the things about likelihood ratios is you need these probabilities. And there's some subjectivity in choosing the probability models that you use, the mathematical tools you use to estimate those. And they said, if you change those, you can get radically different answers. And so it gave them some pause. Now, believe it or not, Lund and I are actually reasonably supportive of likelihood ratios. They did not set out to destroy likelihood ratios, though that is how a lot of their research was portrayed. But the point they make is a good one, and this picture, for those who are repeat attenders here, actually was shown last year at this same meeting by Steve Lund. This is an example that you can think about as being a tool mark examination. Again, it's kind of made up data. So the measure that we're looking at, the feature that we're looking at, is the number of consecutively matching stria. And as in most of my pictures, he's got two distributions here. The numerator is from a series of mated comparisons, that is where the suspect tool made the print. And the denominator is from non-mated pairs, where the suspect tool did not make the print. And they found the number of consecutive matching stria. And you can see among the mated, there typically are a lot, between 7 and 10 matching stria. And the denominator, the non-mated, is very rare to see a large number. Most of the time, you only get 1, 2, or 3 matching stria. There's total mismatch. But Steve asked, what happens if you saw 4? 4 is not super likely under either of these distributions. In fact, in the non-mated, he never saw a 4. But of course, we know a 4 is possible. Why do we know a 4 is possible? Well, we saw a 5, and if a 5 happened, presumably a 4 can happen. In the numerator, we saw 1, I think it's 1, 4. But to create a likelihood ratio, you'd kind of want to estimate how likely are 4s in these two groups. And Steve went on to show that the way we tend to do this, we meaning statisticians in this case, is we fit a curve to these and use the curve to interpolate how likely 4s might be. The problem that Steve and Harry pointed out is there are different curves that you could fit that are all plausible. So you have a black, a red, and a green here. And they're all plausible summaries of the data. Some are maybe better than others, but they're all plausible in the way that Harry and Steve define plausible, which I have problems with, but we won't discuss that. So they are all plausible. And the same thing down here, they don't even look that different on the bottom. But they're surprisingly different because remember, the thing that we're looking at is the height of the curve right here. And they're all near 0, but there's a big difference between 0.01 and 0.001 and 0.0001. Right? Those are really important differences. And so these 3 pictures would give you 3 different likelihood ratios, and they can be very different. In Stephen Howry's paper, one of the things that freaked everybody out is they showed that if you take a very generous definition of plausible, you can even have the likelihood ratio flip sides. That is, a likelihood ratio bigger than 1 supports same source. A likelihood ratio less than 1 supports different source. And they showed for the same data, depending on the model, you could have 100 or a half. So that's a little scary, for me too. But as I said, there's issues about what plausible models are and what they might mean. But their point was, to me, very well taken. Likelihood ratios are not a panacea. They're going to have issues too, and we need to think about that. So here's my summary of likelihood ratios, and then I'll leave you alone. I won't leave, but I'll leave you alone about likelihood. I won't leave you alone. Matt won't let me leave. I won't let you. I'll leave you alone about likelihood ratios, because as I said, I think it's an important topic, which is why I spend so much time on it. Likelihood ratios are the logical way to evaluate and summarize forensic evidence. So why do I say that? Some of the advantages are it makes explicit this notion of we have 2 hypotheses and we try to assess the evidence under those 2 hypotheses. It provides, when it can be done, a quantitative summary of the evidence. That's good. We don't make a non-match decision, which is important. Sometimes in glass, we look at 2 glass samples and we say they don't match completely, but they kind of match, and I'm going to declare them indistinguishable, and we go from there. Better not to make that decision, in my opinion. And the likelihood ratio can handle virtually anything you throw at it. And it's, when done appropriately, quite transparent. That is, you lay out what you assumed, whether you use the green or the red or the black. And in our system, as we discussed this morning, someone else can say, well, you used the green. Why'd you use the green? Isn't it true that if you use the black, you get a likelihood ratio, right? So it's got that advantage. Now, of course, there are huge challenges. Where the data come from to support these pictures is a big problem and a big issue. We need to find these data that tell you how big a difference you might get in a non-matching sample. So Henry Swafford had the advantage of working at a DoD lab and a database full of fingerprints to help build his method. If one wanted to do that for shoe prints, where would the data come from? Unknown. And as we just discussed, the likelihood ratio is a subjective beast. It's not as subjective as expert opinion, maybe, but it's still subjective. There are choices that will be made, and it must be questioned. So that's the end of the likelihood ratio story. Question?
How would you envision that the conclusion would be stated to the jury?
If one was using a likelihood ratio, it's a great question. I think I'm going to leave to David. The 2 comments I would make are, one is, in an ideal world, we would actually show up and say, here's the likelihood ratio and here's what it means. That is, this evidence that I've seen, that I've shown you. I show you the 2 fingerprints. Some match in some places, they differ. The models we have tell us that evidence of this type is 1,000 times more likely if the suspect was the source of the latent print than than a random person was the source of that print. That's the precise way to say it. Now, that's hard to understand for us, very hard to understand for jurors, so a lot of people are trying to understand, to come up with better ways to report that. As I said, one way to think about it is to say, it's a measure of support, of strength of evidence. And so you could try to link it to things people maybe have a better conceptual understanding of. I mentioned this morning, linking it to, for example, how many heads you'd have to get in a row, right? That is, this evidence is 1,000 times more likely. So it provides the same degree of, surprise, if you will, as getting 10 coin tosses in a row. Right? That is the coincidence that would be involved. So that's, but as I said, I think David intends to talk more about that. And that is part of what it says, conveying likelihood ratios to the trier of fact is difficult. That is definitely one of the challenges in using these. So there is a precise mathematical thing that we want to say. That part's clear. But it's definitely not obvious how to do that in a way that juries would find easy to work with. Great, thank you.
Okay.
Oh, question, sorry.
Sorry. How did you view the challenge of masking the presentation presupposes that there'll be no trace, or there are traces everywhere. And, criminals think ahead of science. I don't know where they get that from, but that seems to be the situation.
It's a survival instinct.
What do you do? And how do you analyze evidence where there are cases of masking? For instance, they could approach an object with gloves, or probably put some good on their shoes, or whatever.
It's a great question. To the extent that they leave no trace, if they're successful in the limit, there is no evidence. Everything I'm talking about starts with the evidence. So if there's no evidence, there's nothing to do. If, for example, they are smart enough to know, hey, if I throw some whatever down, my shoe print will look, they march around the room a dozen times, whatever they do. Again, if they change shoes, for example, right, and you capture them, they don't have shoes, So you can't do anything with that. To the degree that masking really adds noise to the data, that is, makes it harder to read, if a technology existed that they could wear that wouldn't avoid leaving a fingerprint, but would automatically smudge the print, say, right? Then that would kind of filter into whatever we were doing. It would kind of mess up the score distributions. They kind of move together. The evidence would be weaker. But a couple of people want to comment, and I need help. So, Matt?
I think that issue is one that we've always faced in forensics, which is, we don't know that we got all the fingerprints that are relevant to the case when we were processing the scene. And so the absence of evidence is not necessarily evidence of its absence.
Yeah, because there are situations where, for instance, in fingerprints, you could capture some traces, but the criminal might not have left any trace because they masked. And you end up prosecuting the people whose traces were found at the scene of crime. And probably get a judgment on the wrong person.
Excellent point. Simon Cole, who's a colleague of mine at UC Irvine, has kind of written extensively about this. That is, there are a variety of errors that happen. When we talk about errors of evidence analysis, we tend to primarily worry about false positives. That is, someone being falsely identified, but that even false negatives are potentially harmful because the false negative means that the person was let go, and typically someone else got blamed, and they just said it was them, they were wearing gloves, so we don't have fingerprint evidence, but we have this other evidence and things like that. But again, these are kind of far from my expertise. So my expertise really kicks in at the point at which we have evidence, how best to characterize and report on that evidence. Yeah.
Score-based likelihood ratio is always going to be positive numbers?
A likelihood ratio, if done correctly, is a positive number. Great question, by the way. I did not say this earlier. It's the ratio of two probabilities, and I should maybe make a little side comment here. The reason we don't call it a probability ratio, and we call it a likelihood ratio, is because if you have a score, or whatever you're measuring, and it's continuous, it no longer makes sense to talk about probability, because what's the probability that my refractive index on a piece of glass is 1.562, instead of 1.56201. So the probabilities become likelihoods. That's a technical point. Please ignore that. Okay, you don't need to know that. Won't be on the test. Okay. But so the things that we're working with are basically probabilities. And you have two probabilities, which are numbers between 0 and 1. Their ratio is between 0 and infinity. Numbers at 1, the likelihood ratio is even. That is, the data, the probability of seeing this evidence is the same under the two hypotheses. So the evidence provides no information to allow me to distinguish between the hypotheses at 1. Less than 1 means the different source is supported by the evidence more than the same source. Bigger than 1 means the same source is supported more. So that's what you end up with. And I once heard someone say this, it seems not symmetric, because 0 and 1 is a pretty small interval, and 1 to infinity is a big interval. But they're actually the same size, remarkably enough, because you just flipped it 1 over. So every point, right? So, so that's kind of the answer to your question. I won't say there aren't things people are doing that might show up looking negative, but they really shouldn't. If they're done correctly, with a score-based or with a real probability model, you'll end up with 2 positive numbers, and the ratio is this kind of relative support. Yeah, Sarah.
So, how do you deal with scaling the likelihood ratio? So, for example, in DNA, a likelihood ratio of 40 would have very real meaning, but for shoe prints, it might have meaning. And so how
So the meaning actually does not change. That, you know, the DNA is just that strong of an evidence, you know, where you're getting numbers in the millions or billions. Although, you know, a strict likelihood ratio would, of course, account for probability of contamination and other things, which might change that number. But ignoring that for the moment, if it turned out that shoe prints were 40 or 100, that would be good to know. And in fact, I told someone the story over lunch, which is my first forensics experience was working with the FBI trying to quantify the strength of bullet-lead evidence. And the way that bullet-lead evidence works is bullets are made primarily out of lead. But the manufacturers add other elements for a variety of reasons, which I don't completely understand. But manufacturers have their own formulas. And so the trace element compositions, the amount of silver or whatever, aluminum, whatever, are found in when you analyze chemically the bullets, maybe helps you identify the manufacturer and perhaps even the time at which it was manufactured. So that was the hypothesis, and they asked us to explore that as a research project. And again, data was an issue. They had 4 boxes of bullets from 4 different manufacturers, 4 boxes of bullets from each, I think. Approximately, anyway. And so we looked at the chemical profiles from those bullets, and we did a number of things to try and figure out what a likelihood ratio might look like. Along the way, we learned a little bit about how bullets are made, and they make from a big vat of material. It's all molten and mixed together with these trace elements, and then they spit it out into long wires and cut it into bullets. And the interesting thing is, they sit around for a while. And then they kind of need to create bullets, and so they grab some, and then they get packed into these boxes of, I've never had a box of bullets, 20 or 50 or whatever, 40 bullets, I think, 40 bullets maybe. And when we analyzed them, what we found was in a single box of bullets, you would have what appeared to be bullets that were manufactured at different points in time. And so when we did our best bet to calculate the likelihood ratio for bullet-lead evidence, I won't go into more detail, we ended up with numbers literally like 2. So, you know, 2 or 3 or something like that. It's based on the chemical profiles we see. A match like this, these 2 bullets that seem to have similar trace element profiles, is twice as likely if they're from the same source, if they were manufactured together, than if they were not, because of the way they're distributed and manufactured and distributed. And that was one of the pieces. It's a long story that we won't go into here. It's just not that probative in that case. And so, you know, the FBI no longer uses bullet-lead evidence. And so we don't know what it is for shoe prints. We may never know, to be completely honest. But if we were able to develop likelihood ratios and find out that they were 100 or 1,000 or 10,000, that'd be great to know. And we would be able to calibrate how much weight to give them in the courtroom relative to DNA. So in cases, especially without DNA, you'd say, okay, you know, 10,000 from the shoes, that's pretty significant. Great questions, though. I'd like to move us on. Let me get through it. So I mentioned 3 ways of analyzing evidence. Everything I've said has been about the second and the third because they're more quantitative. But I want to return to the first, which is where expert opinion is the realm of the coin. Is that what you say? No, the coin of the realm. And so that's the case for most pattern evidence. And so what does case law say about this? Just a reminder, we heard this morning in the context of the firearms analysis. The examiner analyzes the evidence based on their experience, training, and accepted methods in the field. That's exactly what was said this morning. And then when that's done, the evidence reflects the examiner's expert opinion, and the conclusions are typically reported as these categories. For firearms, the speaker this morning said we do identification, exclusion, inconclusive, or unsuitable, something like that. So very similar to what, so that's pretty standard. There may be other categories. You may say, you know, in a shoe, that the shoe matches on size and manufacturer, but doesn't, I don't have any details. Sometimes, and I give one example here, document examiners have their own scale that they use, and they tend to say things like, based on the evidence, the author of the known samples wrote the question sample. That's their strongest statement, analogous to identification. But then they have weaker statements. The author of the known samples it's highly probable that the author of the known samples wrote the question sample. The author of the known samples probably wrote the question, and so they have a total of 9-point scale. 4 positive, inconclusive, and 4 negative statements. But notice that if you read those statements carefully, they kind of bring us back to the Skipper thing. That is, the document examiners are not making statements about the evidence here. They're making statements about the writer, the hypothesis. So it opens up the concerns that we talked about this morning. So I'm not going to revisit that here, but I'm going to focus on places where they're using these smaller scales, identification, exclusion, and so you know the federal rules of evidence for the most part. And David will say more about this. I bring it up just because the key issue here, of course, is reliability, and both of the method and as applied in the case. So 2 cases I want to talk about that raise issues that I think are interesting here. The first is the U.S. versus Glynn, where the defendant was charged with a number of crimes, including murder through the use of a firearm. And we had questions about this morning. The government, at the first trial, there ended up being 2 trials, sought to introduce expert testimony of the firearms analyst that, to a reasonable degree of ballistic certainty, the bullet in the victim and the casings from the scene came from guns owned by the defendant. And the defendant objected that ballistics is not based on sufficiently reliable methods, as required by the Daubert. And so at that first trial, the judge said, that the ballistics, we can't testify that ballistics is a science, would not allow testimony to a certainty, ballistic certainty, and instead said that there is evidence that ballistics analysis is of value in the courtroom, and so that he would allow the examiner to say, based on my analysis, it is at least more likely than not that the bullet and casings came from the guns in question. The first trial ended in a deadlocked jury and a mistrial, and so a second trial was scheduled, and Judge Rakoff noted that there was put out an opinion, I forget what it's called, but an opinion that said, in advance of the second trial, I intend to stand by all of my evidentiary rulings in the first case, except for one small change. And the small change was, he changed it so not to have the at least. So the evidence would be just more likely than not. Okay. So this gets at an important issue in pattern evidence, which is what kind of statements ought we allow based on the evidence that's out there. And when statisticians think about questions like that, they think about reliability and consistency. I put those together because reliability is kind of the more mathematical version of it. But when we say something is reliable, we just mean that it can be consistently measured. That if you do it again, you'll get a similar answer. So you can ask about reliability and consistency in the measurements that are being made. So in the consecutive matching stria or in the image analysis that's being done. You can ask about reliability and consistency in the decisions that are being made. Would the same examiner, given the same evidence at another point in time, make the same decision? Great to know that. Would different examiners facing the same evidence, right? These are kind of, for me, reliability questions, measurement questions, okay? And then none of those first 2 reliability topics touch on whether they got it right. They just say, would you get the same answer? We might all get the same answer, we might all be wrong. That's not good either. But as a starting point, we asked, are we reliable? Do we give the same answer? And as a second, we ask, do we get it right? A couple of examples. The first is from a project I was involved in. When people analyze handwriting, one of the questions one of their basic principles is the more complex the handwriting, the stronger the statement the examiner should be able to make. Logical, lots of whistles and curves in your signature, easier to do the analysis and make a stronger conclusion. Okay? But not all that much data on it. And so working with a colleague at the Los Angeles Police Department, she obtained a bunch of signatures and sent them out to 5 different examiners and asked them to rank them for complexity. How easy or hard would it be to simulate this signature? And you can see the first row is the first signature. The 5 examiners gave different scores. Some gave it 4, some gave it 5, some gave it 3. To be expected. I mean, these are subjective scales. The second, there was more agreement. Everyone agreed it was pretty complex, the 4 and a 5, so on and so forth. But there are a number of statistical approaches to summarizing data like this. The simplest thing to do is just to ask how correlated these two guys are. And so the correlation, if you remember, is a number between 0 and 1. Just like probability, but it's not the same. Correlations actually run from -1 to 1. But a correlation, again, the higher the correlation, the more similar the two scores are as a pair. And these correlated around 0.65, which in the measurement world is considered good. There are some measurements, if we all measured this table and wrote down our numbers and measured 125 tables, and then I looked at how much we agree, we would expect to agree much more than 0.65. It's important to know we would not agree 100%. Right? That is, we don't, you'd start a little bit off to me. So the table's, whatever, 5 feet long, and I might get 61 inches, you might get 59. But if we looked at a bunch of different tables, we would tend to agree at a much higher rate. So that was interesting to me, just as a starting point, right? How repeatable are something like a complexity judgment? Good, but not great. Second interesting point that came out of the study is, for a small amount of signatures, only 7 of them, they actually sent the same signatures back to the same person, I think a month later. And they compared the rankings given by person time 1 and time 2. I don't have the data up here, and there wasn't a lot of it. But what I could discern from that data was interesting to me, because it turned out that me today and me next month are no more alike than me and you. So that's kind of interesting, right? That is, this complexity judgment is a fairly subjective call, and there's a lot of wiggle room, plus or minus 1 point. But it just provides a limitation that we should understand, because if we can't all agree on what's complex, it impacts what happens next when we analyze the evidence. So that was reliability of a measurement that goes into a decision. We can also look at reliability of decisions. And of course, the PCAST study made a strong endorsement for black box studies. And one example that PCAST found valuable, and which I also think was good work, is this study by Ulrich et al. On fingerprint decisions. So they had examples where they knew the truth, a latent print and a known print, some of which were matched, some of which were not. And I forget the numbers, but there was, I think, 69 examiners and 700 prints altogether. And not every examiner did every print, but they had a lot of comparisons. And when you do a study like that, you get some information now, both about reliability. They could see whether the examiners were giving the same answers. But also, in this case, because you know the truth, you can see whether they're getting it right or not. And they found, out of 6,000 or so comparisons, the false positive rate was about 1 in 1,000. There were 5 false identifications. And the false negative rate was 7.5%. And one of the things I personally like about science and statistics and all this stuff is, you learn stuff. It's just good for you. You learn stuff. In this instance, forgetting about the false positive rate, I think the examiners themselves were surprised at the false negative rate. The authors report that most of the examiners that participated in the study, they were given a questionnaire, were very confident that they had never made a false negative. Yet, in this study, 80% of them had a false negative. Right? So the rate was higher, and it was the false negatives were pervasive. The false positives, out of 170 examiners, only 4 or 5 of them made false positives. But they almost all made false negatives. And it's not bad. I mean, that's our system of justice maybe is happy this way. But it's important to think about this. This is the point where the statistician steps away. That is, what's the right trade-off between false positives and false negatives? I don't know that. That's not my call. That's society's call at some level. The Glynn case was about firearms. And so here are results from a study that was done and published in 2014 on cartridge cases. So this is very similar to the fingerprint study we just described. It's interesting to see here that the false positive rate here was higher, it was 1.5%. And the false negative rate was lower, was 0.4%. So again, I find the data very valuable in knowing, and it allows us to, the two places appear to have different cultures, the two disciplines, right, in terms of the trade-offs. So that's the kind of idea of a black box study, a study with known truth, which examples are put into the system, judged, and the answers assessed as a way of learning about the process. So we can then return to the Glynn case. And in terms of coverage, don't want to talk a ton about the PCAST report, so I'm going to leave that aside. But say a little bit more about the judge's thinking in the case. The definition of match, which someone asked the firearms analyst this morning to talk about the AFTI definition of what an identification is. And the AFTI definition of identification basically says that there's a match when there's a sufficient amount of agreement in the features and more than would be, and no more disagreements than would be expected, blah, blah, blah. So there's a bunch of language like that. But the judge in this case cited, relying on a notion of sufficient agreement when it's a subjective judgment, this judge said he would not call it science at that point, that it's an opinion. And again, the judge also found concerning the lack of standards in ballistics. But he said there's evidence out there, and he cited the 2008 NRC ballistic imaging report, that ballistic images could be useful in identifying source of guns. And so he said there's reason to leave it in, but not allow statements that implied strong science. And based on past experience, statements about matches being certain or about error rates of methods being 0, that the court had a role to play in alerting the jury to the limitations. And that's what led to his 2 statements, at least more likely than not, and then the second trial, just more likely than not.
He's the only judge.
I know. But I need a reason to talk about this. But I think the question going forward, of course, is what the testimony really ought to look like. And obviously, quantification would help maybe bring everyone together. But what happens in the interim is an ongoing discussion. The last case I want to discuss is, again, in one of these kind of special situation, but it's a special situation that's useful for me in terms of talking about what happens when we have expert opinion. So this is a case that occurred in the state of North Carolina in which a pizza delivery driver was assaulted, and the history of the case is long, which I'm not going to go through, but they ultimately figured out that the order for the pizzas came not from, the pizzas were being delivered to an abandoned house. And they were able to track down, the order was made online, and the source of the order was not too far away, and they went to that address and found the pizza boxes and the chicken wing boxes. Got fingerprints off of them, also fingerprints from the car, and they matched the suspect. Okay, so that's what the case was about. And at this point, where the McPhaul case shows up is the federal rules of evidence require reliable principles and methods, but also reliably applied to the facts of the case. And the McPhaul case focuses attention on Part D here, rather than part C. That is, for fingerprints, we have a very long history, and the study that I just cited that suggests, hey, experts can do very well at identifying fingerprints, so we can leave that in, but we still have to ask whether it was done well in the case at hand. So here's all the charges. That's one of the worst acronyms I've ever seen. So once again, we have this trial, and the defendant moved at the trial to suppress the evidence recovered from the residence, but the court denied it, and the defendant was found guilty. So the defendant appealed on several issues. Again, as is the case for the other cases we've talked about, most of the issues don't have anything to do with me in statistics or measurement, so I don't talk about them. But in particular, one of the issues the defendant appealed on is that the court made a mistake by allowing the state's expert to testify on the fingerprint evidence. And the court ultimately agreed on that, but found the error was not prejudicial, so did not change the decision. So let me go back and say a teeny bit more about that case and what the judge was kind of saying in the decision. The basic statement was, as per Daubert, the trial court can be reversed with respect to evidence only for abuse of discretion. That is, a finding that the ruling was not supported by reason. And in the context of this case, what the judge cited was two pieces of the story. Early on, the expert was brought in and certified as an expert based on experience, training, passing of proficiency test, and the like. The defense did not object. The expert was seated, and the fingerprint analyst testified how fingerprint analysis works. And so you see some of the types of language we just talked about. They look at the two prints side by side. When there's enough sufficient characteristics and sequence of similarities, that's when they make an identification decision. And then towards the end, as I understand it, they went back and as part of the wrap-up to say, okay, now let's look specifically at the evidence in this case. Can you tell me, show the jury how the comparison works here for these items? And the analyst says, yes, these match. And when asked upon what is that conclusion based, my training and experience in looking at the minutia with the two fingerprints, is that right? That's correct, the process I explained earlier. And what the judge found objectionable was there's no reference to what exactly in the two prints that were being compared was the analyst testifying to. In talking to other people about this, to some extent, you never quite know what's going on. The person may have thought it's self-evident that because I told you how it works, I was looking at similarities and features, but the judge appears to have been looking for, as you can see on this feature, things here and there. So that's what, in this case, led the judge to say it had not been applied appropriately in this case because there was nothing specific to this case. So that's basically all I have. I have a conclusion slide, which I attempt to kind of tie together all the things I've talked about. In particular, we start with the notion that Daubert makes the judge the gatekeeper, and I tried to pull together today a number of cases that talk about the role of probability and statistics in all forensics, but especially in the pattern matching disciplines. And in particular, I ask you to think about the three different ways that one can think about evidence. That is expert opinion, which we talked about this afternoon, and is the state of the art in the pattern disciplines. Match probabilities or coincidental match probabilities, which you can think about happening in DNA and some other places, and the likelihood ratio. And to me, they all have in common that one should be accounting for these two hypotheses, same source, different source in my world, and that we should be explicit about the modeling, the reasoning that we're doing. There should be empirical support, and to me, that means things like the black box studies. That is, there tends to be empirical support if you can build a likelihood ratio or coincidental match probability. In expert opinion, what does empirical support look like? The kinds of studies we looked at are one example. So I'm going to stop there. I'm early, and we have time for questions galore on any of the topics I've talked about. But I'll stop there. Thanks.
Are there any questions for Al?
Yes.
Well, this is more of a comment. There was a point that was made from the audience that Judge Rakoff's decision limiting firearms testimony was the only one of its kind. I don't think that's accurate. I think there have been decisions across the country with similar rulings, including in federal court in Maryland, in Chicago, and I believe in Florida also. So I think that this is there is a trend to be sort of sophisticated in thinking about these kinds of testimony and how it should be limited.
Thank you. That's a great point. David Kay has an article on the subject, and he reviews, I don't know if they're the same decisions, but some of those decisions, and it's certainly more than an N of one. I think the evidence is still allowed predominantly as testified, but it is, I think, as you point out, and as I tried to point out, I think part of the conversation that ought to be happening now is, what can science say about this? How can science inform this? Thank you.
Did you say you were going to put your slides up, or do we have to contact, all of us have to contact you individually?
Plan B works, but I don't know, Matt, is there a mechanism?
Yes. I'm going to ask all the speakers if there were slides that didn't make it into your materials, so maybe go ahead and submit those either to me or to Courtney, and then we'll send them out to you.
So they're now on the computer here. Thank you. I did close with my email, so because you can ask me directly if you want. Yes.
My memory was last year when Swafford presented every likelihood ratio for an identification was like either 90,000 or 96,000. And do you know if that was limited by the number in the database? Because I think he's using like a smaller database than...
Yeah, he's certainly using a smaller database. And he's also, a little bit into the weeds of the ratio that he's actually computing. I'll show you one thing which would push in the direction that you're observing. So, sorry. It's always nice to have a picture. But it's further back than I thought it was. Almost there. So the likelihood ratio I think of as the height of these two curves. In fact, what FR stats does is it kind of says, you know what, if I got this height, if I got this score, let me compare the chances of getting this or something bigger from the known non-matches and this or something smaller from the known matches. And that was an attempt on his part, I believe, to be somewhat conservative. That is, you're adding in not just what you saw, but other evidence that would have been more in that direction. And that would tend to have generally speaking, the effect of keeping the likelihood ratios from going astronomically high. He made a few choices to try and do that. Now, it's impossible to make a choice that you know will go in a certain direction, is the truth of it. That is, anything you do, we have techniques for how these curves come to pass, and they require choosing a specific distribution to build from. And he tried to build one that would have heavy tails rather than light tails. We talk about heavy tails as how much probability is out here. And a light tail would go down very quickly and have no probability out here. And he thought it was important to have heavy tails to allow for things that he hadn't seen because he has a limited amount of data, for example. So I don't know for sure. I'm not that expert in it. And in particular, it's been developed further than when I saw it. So I don't know exactly where he ended up. He had he did not run off anything like a giant APHIS database. They ran off, I think, 50,000 prints or something like that. Good question. Thank you. Oh, sorry. Yes.
I've heard this argument before. I'm still not sure I can wrap my head around it when it comes to likelihood ratios. The idea of the two comparisons of probabilities being the exhaustive set of worlds that could happen, and to bring it back to baseball, an analogy I've heard that I use is it's the comparison of the National League winning the World Series versus the American League, when we know one of those two things will happen, versus the Mets. over the coast.
So just to have something to point at. Your question is a good one. It happens to be one of the places where some statisticians are more sticklers than others. That is, I've split up the world in the way that you describe. There's only two possibilities. Either the suspect is the source, my H sub S, or the suspect is not the source, H sub D. And so these are the terms that's used is mutually exclusive. That is, if one of these is true, the other can't be. And exhaustive. They cover the entire world. Okay. Suppose instead, it's an Agatha Christie novel, okay? And there's 12 people in a mansion, and a murder happens, okay? So now, maybe your hypothesis set looks a little different, okay? Instead of this, we know the butler did it, but let's ignore that for the moment, okay? So instead of having H sub S for the suspect and H sub D for someone else, you might have H sub 1, that it was person 1 at the dinner party, and H sub 2, that it was person 2, and H sub 3, right? And then we're not up to this scientifically, but suppose we were, and we could compute. How likely is it that I would see this fingerprint evidence if it was person 1? This degree of match between the known and the question. I could do that for person 2, and so on and so forth. You could actually do a bunch of likelihood ratios. There's a likelihood ratio comparing person 1 to person 2. There's a likelihood ratio comparing person 7 to person 8, and so on and so forth. The problem with those likelihood ratios for some people is they don't look like this. That is, it's a ratio of two probabilities, but they're not mutually exclusive and exhaustive. Both person 7 and person 8 could be extremely unlikely, because we don't know that one of them did it. So some people say you should not use likelihood ratios in that case because you don't have mutually exclusive and exhaustive. I would not say that. That is, the likelihood ratio is what the likelihood ratio is, to sound a little Dow. It is what it is. If you compare only those two hypotheses, then that's what you get back, which is whether the evidence supports 7 versus 8. Okay, and it could be that 7 is, 1 in 10,000, and 8 is 1 in a million. In which case, there'd still be a likelihood ratio. I should have picked numbers I could divide in my head, but I think that's 100. So the likelihood ratio in that case is 100. It says the evidence that I've seen is 100 times more likely if 7 is the person than if 8 is the person, but it obfuscates the notion that, in fact, neither one of them is very likely. So, that's kind of what I'd say about it. It's, if they're not mutually exclusive and exhaustive, if you're in the Agatha Christie, then you have to be very careful in thinking about what you want to do. In that case, we would almost certainly want to look at all of the 12 possibilities and see where the evidence points. Thank you for asking that.
Out there.
Yep.